Earth is a dynamic and ever-changing planet, driven by a complex interplay of natural cycles that have shaped its history and continue to influence its future. From the rhythmic dance of the seasons to the powerful forces of tectonic movement, these cycles are integral to life as we know it. Yet, as we move deeper into an era marked by rapid environmental changes and technological advancements, the question looms: how will shifts in Earth's cycles affect us? This journey through Earth's natural, geological, and extraterrestrial influences offers a glimpse into the interconnected systems that govern our world, and the challenges and opportunities they present for humanity. Milankovitch cycles. The Milankovitch cycles are a cornerstone in understanding Earth's climatic rhythms. These cycles, named after Serbian mathematician Milutin Milankovitch, explain how subtle changes in Earth's orbit and axial tilt influence global climate patterns over tens of thousands of years. They serve as the planet's long-term metronome, orchestrating the advance and retreat of ice ages. The first of these cycles is orbital eccentricity, which describes how Earth's orbit shifts from nearly circular to more elliptical over a period of about 100,000 years. When the orbit is more elliptical, the variation in solar energy Earth receives between its closest and farthest points from the Sun increases, amplifying seasonal contrasts. These changes can tip the balance between glacial and interglacial periods, shaping the advance of ice sheets and influencing sea levels. The second cycle, axial tilt, or obliquity, occurs over a 41,000-year period. Earth's axial tilt varies between about 22.1 and 24.5 degrees. This tilt determines the intensity of seasons. A greater tilt means more extreme seasons, hotter summers and colder winters. Conversely, a smaller tilt results in milder seasons, creating conditions favorable for ice sheet growth. Lastly, the wobble in Earth's spin, called axial precession, happens every 26,000 years. In relation to Earth's path, this wobble changes the timing of the seasons, which changes weather trends in a subtle way. For instance, glaciers are more likely to form when winter is in the northern hemisphere at the farthest place in Earth's path from the Sun. This is because cooler summers make snow last all year. Complex feedback loops are made when these processes interact with each other. Glacial periods are more likely to happen when eccentricity is high and tilt and precession are good. On the other hand, interglacial periods are most common when the cycles line up to reduce the difference between seasons. The Milankovitch cycles tell us a lot about the past and future temperature of Earth. Ice cores from Antarctica and Greenland show that these cycles are directly linked to changes in temperature over time. Scientists can predict possible changes in the climate and get ready for their effects by studying them. Plate tectonics and climate shifts. At the heart of this connection lies the concept of continental drift. As tectonic plates move, they reposition landmasses, altering how sunlight is distributed across the planet. When continents cluster near the equator, they absorb more solar energy, fostering warm climates. Conversely, when landmasses drift toward the poles, ice sheets can expand, driving global cooling. The supercontinent cycle, which sees landmasses periodically coalescing into supercontinents like Pangaea before breaking apart again, exemplifies this process. These shifts profoundly influence Earth's climate, triggering ice ages and warming periods. Mountain building or orogeny is another significant tectonic process that shapes climate. When plates collide, they create towering mountain ranges, like the Himalayas or the Andes. These mountains disrupt atmospheric circulation, forcing air to rise and cool, leading to precipitation on the windward side and arid conditions on the leeward side, a phenomenon known as the rain shadow effect. Additionally, as mountains erode, they expose fresh rock that reacts with atmospheric carbon dioxide, acting as a long-term carbon sink. This weathering process can significantly lower global temperatures over geologic timescales. The Earth's ocean currents, which control the temperature, are also affected by tectonic shifts. The paths of these currents are set by where the countries are located, which changes how heat is spread around the world. For example, the Isthmus of Panama closed off the link between the Atlantic and Pacific Oceans about 3 million years ago. This made the Gulf Stream stronger. By moving heat and wetness to the polar regions, this change helped start the Ice Age cycles, Subduction zones and volcanic activity associated with plate boundaries also impact climate by releasing carbon dioxide and other greenhouse gases. Over millions of years, these emissions contribute to the greenhouse effect, warming the planet. On shorter timescales, massive volcanic eruptions can inject aerosols into the atmosphere, reflecting sunlight and causing temporary cooling. The interplay between these processes underscores the dual role of tectonic activity in driving both warming and cooling trends. Ocean currents and the Thermohaline circulation. Deep within Earth's oceans lies a vast and intricate system of currents that operates like a global conveyor belt, redistributing heat, nutrients, and gases across the planet. Known as the Thermohaline circulation, this interconnected network is driven by differences in water temperature, thermo, and salinity, haline. It is one of the most critical regulators of Earth's climate, stabilizing temperatures and fostering life across continents and oceans. The Thermohaline circulation begins in the polar regions, where cold, dense water sinks to the ocean floor. This process, known as deep water formation, occurs primarily in the North Atlantic and near Antarctica. As seawater cools and sea ice forms, it leaves behind salt, increasing the salinity and density of the surrounding water. This denser water sinks and flows along the ocean floor, spreading out across the globe and drawing in warmer surface waters to replace it. This movement creates a conveyor belt-like system that spans thousands of kilometers. For example, warm surface waters from the tropics travel northward via the Gulf Stream, warming the coasts of Europe. As the water cools, it sinks and begins its journey back toward the equator along the ocean floor. This cycle not only redistributes heat, but also helps regulate global climate by moderating extreme temperatures. This method is important for more than just distributing heat. Ocean currents are very important for marine ecosystems at all depths because they move air and nutrients around. Upwelling currents bring nutrient-rich water to the surface, which is needed by phytoplankton, which are tiny creatures that are at the base of the ocean's food chain. As the seas take in huge amounts of carbon dioxide from the air, these processes keep fisheries, wildlife, and even world carbon sequestration going. However, the Thermohaline circulation can be broken. Changes in the climate caused by people are very dangerous to its security. As temperatures rise and the polar ice melts, rainwater floods into the seas. This lowers the saltiness of the water and makes it harder for deep water to form. If this balance changes a lot, it could make parts of the circulation weaker or even stop them. The effects would be huge. Winters could get colder in Europe, storms could get stronger in the tropics, and changes to sea environments could threaten food security around the world. Historical evidence points to the fragility of this system. During the Younger Dryas period, approximately 12,000 years ago, a sudden influx of fresh water from melting ice caps is believed to have temporarily halted the Thermohaline circulation, plunging parts of the northern hemisphere into a mini ice age. Today, scientists warn that similar disruptions could occur if current warming trends continue unchecked. El Nino and La Nina phenomena. These events, which are part of the larger El Nino Southern Oscillation (ENSO) cycle, arise from temperature fluctuations in the Pacific Ocean. Their influence reaches far beyond the Pacific, triggering dramatic shifts in weather, ecosystems, and economies across the globe. Ocean temperatures and the flow of air in the atmosphere affect each other, which is what ENSO is all about. During an El Nino event, warm water that normally rests in the western Pacific moves eastward toward the central and eastern Pacific. This stops the normal rising of cold, nutrient-rich water along the coast of South America. This heat changes weather trends all over the world by messing up the flow of air in the atmosphere. La Nina, on the other hand, is the opposite phase. It is marked by unusually cold ocean temperatures in the central and eastern Pacific, and stronger upwelling along the same shoreline. The impacts of El Nino are felt on every continent. It often brings heavy rains and flooding to the western coasts of the Americas, while regions like Australia, Southeast Asia, and parts of Africa experience droughts and wildfires due to suppressed rainfall. These weather extremes affect agriculture, water resources, and infrastructure, posing significant challenges to both natural ecosystems and human societies. For instance, during the strong El Niño event of 1997 to 1998, global economic losses from flooding and drought reached tens of billions of dollars. La Nina, while often seen as El Niño's counterpart, brings its own set of challenges. Enhanced rainfall and hurricanes are common in some regions, while others experience dry conditions. The 2010 to 2012 La Nina event, for example, exacerbated droughts in East Africa, leading to severe food insecurity for millions of people. At the same time, Australia experienced record-breaking floods, highlighting the duality of its impacts. ENSO cycles also ripple through ecosystems. In the Pacific Ocean, El Niño events can devastate marine life by disrupting the nutrient supply brought by upwelling currents. Fish populations such as anchovies and sardines may plummet, affecting entire food chains and the fishing industries that depend on them. La Nina, conversely, can enhance marine productivity in some areas, but often at the cost of extreme weather events on land. A big goal of climate research is to understand and predict ENSO events. Forecasts have gotten better thanks to progress in satellite technology, ocean buoys, and computer models. This has helped governments and businesses get ready for the effects. Early warnings can help lessen damage by, for example, letting farmers change when they plant, or helping towns build stronger storm defenses. But these statements are getting harder to make because climate change is having a bigger effect on the world. Warmer temperatures may make ENSO trends stronger or change them in ways that are hard to predict. Atmospheric rivers and extreme weather events. High above the surface, in the vast expanse of the atmosphere, invisible rivers of moisture flow with tremendous energy, shaping weather patterns and delivering much-needed precipitation or catastrophic floods. Known as atmospheric rivers, ARs, these narrow bands of concentrated water vapor transport vast quantities of moisture from the tropics to higher latitudes, acting as a critical component of Earth's hydrological cycle. However, the increasing intensity and unpredictability of these systems due to climate change are raising concerns about their role in extreme weather events. Atmospheric rivers are often described as the fire hoses of the sky. Stretching thousands of kilometers long and only a few hundred kilometers wide, these phenomena can carry up to 15 times the water volume of the Mississippi River, though this moisture exists in vapor form. When an atmospheric river encounters a mountain range or a cold front, the moisture condenses and falls as precipitation, leading to intense rain or snow. The most well-known type of atmospheric river is the Pineapple Express, which originates near Hawaii and transports warm, moisture-laden air to the western coasts of North America. These events are vital for replenishing water supplies in arid regions, particularly in places like California, where atmospheric rivers provide up to 50% of the state's annual rainfall. However, the dual nature of these systems means they can also unleash devastating floods, landslides, and infrastructure damage. The increasing intensity of atmospheric rivers is one of the most concerning consequences of climate change. As global temperatures rise, warmer air holds more moisture, approximately 7% more water vapor for every degree Celsius of warming. This amplifies the amount of moisture available in atmospheric rivers, increasing the likelihood of extreme precipitation events. Regions that were once reliant on these systems for steady rainfall are now experiencing more erratic patterns, with prolonged dry spells punctuated by intense storms. Recent examples highlight the destructive potential of atmospheric rivers. In 2021, British Columbia, Canada, faced catastrophic flooding caused by a series of ARs that dumped record-breaking rainfall over several days. The resulting floods washed away highways, inundated farmland, and forced thousands of people to evacuate. Similarly, California's Oroville Dam crisis in 2017 was exacerbated by heavy rainfall from atmospheric rivers, which overwhelmed the dam's spillway and posed significant risks to downstream communities. The effects of atmospheric rivers extend beyond precipitation. These systems influence snowpack accumulation in mountainous regions, which acts as a natural reservoir for water supplies during warmer months. However, as ARs bring warmer air, they can cause rapid snowmelt, leading to sudden floods and reducing the snowpack available for summer use. This poses a challenge for water resource management in regions dependent on snowmelt-fed rivers. ARs also play a role in disrupting ecosystems. Prolonged heavy rains can lead to soil erosion, loss of vegetation, and habitat destruction. In marine environments, excessive runoff from AR-induced flooding can introduce pollutants and nutrients into coastal waters, triggering harmful algal blooms and affecting aquatic life. Efforts to monitor and predict atmospheric rivers are advancing, with satellites, weather models, and ground-based observations providing valuable data. Atmospheric river intensity scales, similar to hurricane categories, are being developed to help communities prepare for these events. These scales consider both the duration and the amount of moisture carried by the AR, offering a clearer picture of potential impacts. Adapting to the challenges posed by atmospheric rivers requires a combination of infrastructure improvements and ecosystem management, enhancing flood defenses, restoring wetlands to act as natural buffers, and investing in water storage systems can mitigate the risks associated with extreme precipitation. Additionally, integrating atmospheric river forecasts into disaster preparedness plans can help reduce the human and economic toll of these events. Atmospheric rivers are both a lifeline and a threat, reflecting the complex interplay of natural systems in a changing world. As we grapple with the realities of climate change, understanding and managing these phenomena will be essential for safeguarding water resources and protecting vulnerable communities. Volcanic activity and its cycles. Volcanoes act as pressure valves for Earth, releasing vast amounts of energy and material trapped beneath the planet's crust and mantle. Volcanic activity, while typically perceived as destructive, plays an important role in altering the Earth's climate and ecosystems. The eruption cycle, which ranges from small-scale lava flows to enormous explosive occurrences, reveals the complex linkages between the planet's subsurface and surface. Volcanic eruptions are not random, but follow patterns driven by geological processes deep within the Earth. The distribution of volcanoes across the planet reflects the boundaries of tectonic plates, where most volcanic activity occurs. Along divergent boundaries, such as the Mid-Atlantic Ridge, magma rises as plates pull apart, creating new crust. At convergent boundaries, where one plate subducts beneath another, magma forms as the descending plate melts under intense pressure and heat. Hotspots, like those under Hawaii, represent another type of volcanic cycle, where plumes of magma rise through stationary weak points in the crust. The climatic effects of volcanic eruptions are profound. When volcanoes erupt, they release not only lava and ash, but also gases like carbon dioxide, CO2, sulfur dioxide, SO2, and water vapor. While CO2 contributes to long-term warming, SO2 has a cooling effect in the short term. When ejected into the stratosphere, sulfur dioxide combines with water to form sulfuric acid aerosols, which reflect sunlight and temporarily lower global temperatures. Historical examples illustrate the dramatic impact of volcanic eruptions on Earth's climate. The eruption of Mount Tambora in 1815 caused the year without a summer in 1816, as ash and aerosols in the atmosphere cooled the planet, leading to crop failures and famine across the northern hemisphere. Similarly, the 1991 eruption of Mount Pinatubo injected millions of tons of sulfur dioxide into the stratosphere, reducing global temperatures by about 0.5 degrees Celsius, 0.9 degrees Fahrenheit, for several years. Volcanic activity also influences longer-term climate cycles. Over millions of years, volcanic eruptions have contributed to periods of both warming and cooling. For instance, the massive outpourings of basaltic lava during the Deccan Traps eruptions in ancient India are thought to have played a role in the mass extinction event that ended the reign of the dinosaurs. Conversely, the release of CO2 from volcanic activity has contributed to periods of global warming, counteracting cooling trends. Beneath the surface, volcanoes act as engines of chemical recycling. Subduction zones return carbonates and water-rich minerals to the mantle, while volcanic eruptions release these materials back to the surface. This continuous exchange is part of Earth's carbon cycle, balancing the planet's long-term climate system and sustaining life. But volcanic hazards aren't just global climate changes. They can also have devastating local effects. Pyroclastic flows, lahars, and ashfall are immediate dangers to communities near volcanoes. Ash clouds can stop flights, as happened during the 2010 eruption of geological in Iceland, which grounded flights across Europe for weeks. Keeping an eye on and predicting volcanic activity have become important ways to lower risks, with satellites, seismometers, and gas sensors giving early warnings of possible eruptions. Volcanic activity cycles show us how changing Earth is and how it can both make things and destroy them. Even though volcanoes can make it hard for people to live and change the weather, they also renew landscapes, feed the soil, and keep the processes going that make Earth livable. Earth's magnetic field reversals. Earth's magnetic field is a protective shield, a dynamic force generated deep within the planet's outer core. Its primary function is to deflect solar wind and cosmic radiation, shielding life on Earth from harmful particles. Yet, the magnetic field is far from static. It undergoes periodic reversals, where the north and south magnetic poles switch places. Geomagnetic reversals are driven by the dynamo effect, the process by which Earth's liquid outer core, composed of molten iron and nickel, generates a magnetic field. As the core's turbulent motions churn the molten metals, they produce electric currents, which in turn generate magnetic fields. Occasionally, this dynamo system becomes unstable, leading to a weakening and eventual reversal of the magnetic poles. The times between these reversals are not regular. They happen every tens of thousands to millions of years. The Bruniss-Matuyama reversal, which was the most recent big reversal, happened about 780,000 years ago. Scientists studying the fossil record have found more than 180 reversals in the last 83 million years, but no clear trends have been seen. The Earth's magnetic field doesn't just flip overnight during a reversal. The process can last for thousands of years. During that time, the magnetic field weakens, breaks up into many poles, and slowly rearranges itself. During this time of change, there are worries about the field's ability to protect Earth from cosmic radiation. If the magnetic field is weaker, more charged particles could reach the atmosphere. This could make people and other living things more exposed to radiation on the surface, which could hurt them. Evidence from ancient rocks, ice cores, and sediment layers provides clues about the impacts of past reversals. Fossilized magnetite in rocks records the orientation of Earth's magnetic field at the time of their formation, offering a timeline of reversals. Studies suggest that while reversals might coincide with increased radiation levels, there is no direct link between reversals and mass extinction events, indicating that life on Earth has largely adapted to these changes. But in this day and age of technology, the effects of a magnetic reverse might be worse. A lot of modern infrastructure like power lines, satellites, and communication networks depends on electric systems that could be harmed by more sunlight. Geomagnetic storms could happen during a turnaround because the magnetic field is weaker. These storms could damage satellites and mess up GPS systems. For example, the geomagnetic storm of 1989 caused a huge blackout in Quebec, Canada. This showed how power systems can be damaged by magnetic changes. While a full reversal may be thousands of years away, there is evidence that Earth's magnetic field has been weakening over the past 2 centuries. The South Atlantic anomaly, a region where the magnetic field is particularly weak, has grown in size, raising questions about whether we are witnessing the early stages of a reversal. Ongoing studies aim to determine whether these changes are part of a normal fluctuation or a precursor to a more significant event. Despite the unknowns, a lot of progress has been made in studying and keeping an eye on Earth's magnetic field. Changes in the field's strength and shape are tracked by satellites like the SWARM project from the European Space Agency. This gives scientists studying the dynamo effect and its effects useful information. These findings are very important for getting ready for problems that might come up because of changes in the magnetic field. Earth's core dynamics and magnetic field generation. The Earth's core is what makes many of its moving processes work, like plate tectonics and the magnetic field. This area is mostly made up of iron and nickel and has a solid inner core and a flowing outer core. Earth's geodynamo is made when heat, pressure, and motion in the core interact with each other. This is a key process for creating the planet's safe magnetic field. The liquid outer core, swirling with molten metals, acts as a conductor. As heat from the inner core causes convection currents, These movements generate electric currents. In turn, these electric currents produce magnetic fields, which collectively create Earth's magnetosphere. This dynamic process is not static. Fluctuations in temperature and composition lead to variability in the magnetic field's strength and structure. Heat transfer from the core also powers mantle convection, which drives plate tectonics. This connection between the core and Earth's surface underscores the interconnected nature of Earth's systems. For example, hotspots like Hawaii trace their origins to mantle plumes, which are fueled by the heat escaping from deep within the planet. Changes in the Earth's magnetic field have left their mark on its past over geological ages. Magnetic lines on the ocean floor, which were made when the sea floor spread, show how Earth's magnetic poles move back and forth over time. These patterns help us understand how the core works and how Earth's magnetic shield has changed over time. The strength of the magnetic field has not been constant. During periods of weakening, such as before geomagnetic reversals, Earth's atmosphere becomes more vulnerable to cosmic radiation. This increased exposure can affect everything from the chemistry of the upper atmosphere to the genetic makeup of living organisms. Solar cycles and their impact. The Sun, a life-giving force for Earth, is far from constant. It undergoes an 11-year solar cycle marked by periodic variations in solar activity, including the number of sunspots, solar flares, and coronal mass ejections, CMEs. These cycles, driven by the Sun's magnetic field, influence not only Earth's climate, but also its technology-dependent infrastructure and atmospheric dynamics. The solar cycle serves as a stark reminder of the interconnectedness between our planet and its cosmic environment. At the center of the solar cycle is the Sun's magnetic generator, which makes magnetic fields by moving plasma inside the Sun. Sunspots are dark, cooler spots on the Sun's surface where magnetic fields are very strong. They appear on a regular basis because of this dynamo process. Solar maximums are times when the Sun is very active. During these times, the number of sunspots peaks, and the Sun sends out more light and high-energy particles. Conversely, during solar minimum, sunspots are scarce, and solar activity diminishes. These fluctuations in activity affect Earth in numerous ways. Increased solar radiation during solar maximum enhances the ultraviolet, UV output, which in turn influences the stratosphere, including the ozone layer. This dynamic interaction plays a subtle role in shaping global weather patterns and climate variability. The aurora borealis, northern lights, and aurora australis, southern lights, are two of the most clear and easy-to-see signs of solar activity on Earth. These amazing shows happen when charged particles from the Sun connect with Earth's magnetic field and hit molecules in the atmosphere, releasing energy in the form of light. Solar activity that is very high can be amazing, but it can also be dangerous. Solar flares and CMEs, both products of intense magnetic activity, release vast amounts of energy and charged particles into space. When these events are directed toward Earth, they can disrupt communication systems, GPS navigation, and power grids. The Carrington event of 1859, the most powerful geomagnetic storm on record, caused widespread telegraph failures and even fires in communication stations. If a similar event were to occur today, it could wreak havoc on modern infrastructure. In addition to causing short-term problems, solar cycles may also have an effect on long-term temperature changes. There may be links between times when the Sun isn't active, like the Maunder minimum, 1645-1715, and cooler temperatures around the world. During this time, there was also the Little Ice Age, a time when winters were colder and growing seasons were shorter in the Northern Hemisphere. Solar activity is not the only thing that affects the climate, but changes in it can make or weaken current trends. Understanding and predicting the solar cycle has become a critical area of research. Observatories like NASA's Solar Dynamics Observatory, SDO, and the European Space Agency's Solar Orbiter monitor the Sun's activity, providing valuable data for forecasting solar storms. These forecasts are essential for protecting satellites, astronauts, and power grids from the impacts of solar events. As our technology gets better, it becomes more important to be ready for problems caused by the Sun. More radiation protection is being built into satellites and vehicles, and governments are working on rules to lessen the effects of geomagnetic storms. But a lot about the solar cycle remains unknown, like how it decides how strong it is and how long it lasts. Lunar influence on Earth's tides. As Earth's steady partner, the Moon has a huge effect on our planet. It changes the oceans, the rocks, and even the rhythms of life. The Moon's part in controlling Earth's tides, which is caused by gravity interactions, is the most obvious and important of these effects. The old dance between Earth and its Moon has had a big impact on the Earth's environment and will continue to do so as the Moon slowly moves away. Tides are the result of the Moon's gravitational pull on Earth's oceans. While the Sun also contributes to tidal forces, the Moon's proximity to Earth gives it a much greater impact. The Moon's gravitational force creates a bulge in the oceans, one on the side facing the Moon and another on the opposite side, due to the interplay of gravitational pull and the centrifugal force of Earth's rotation. These bulges result in high tides, while areas perpendicular to these bulges experience low tides. The twice-daily rise and fall of the tides affect coastal ecosystems in myriad ways. Intertidal zones, the areas exposed during low tide and submerged during high tide, are among the most dynamic and biologically productive habitats on Earth. These zones provide a home for diverse species, from barnacles to crabs, all adapted to withstand the extremes of exposure and immersion. Tidal forces are also a major driver of ocean circulation. The energy generated by tides helps mix ocean waters, redistributing nutrients and oxygen throughout the water column. This mixing supports marine ecosystems and regulates Earth's climate by influencing heat distribution across the planet. Without the Moon's tidal forces, these essential processes would be significantly diminished. The Moon has an effect on the Earth's waves that goes beyond its gravity. Over time, tidal friction between Earth and the Moon slowly moves Earth's rotational momentum to the Moon. This makes Earth spin slower. This slowing down has an interesting effect. Earth's days have been getting longer since the planet was formed. Hundreds of millions of years ago, a day was only about 18 hours long, while today it's 24 hours long. Simultaneously, the Moon is receding from Earth at a rate of about 3.8 centimeters, 1.5 inches per year. This gradual separation has implications for the future. Over billions of years, the weakening tidal forces will lead to less pronounced tides, altering the dynamics of coastal ecosystems and ocean circulation. The Moon's eventual distance could even render solar tides more dominant, fundamentally changing Earth's tidal behavior. Human history is deeply intertwined with the tides. Coastal civilizations have relied on tides for navigation, fishing, and trade for millennia. Ancient cultures, such as those in Mesopotamia and the Pacific Islands, meticulously tracked lunar phases to predict tidal patterns, integrating this knowledge into their daily lives and mythologies. The Moon's role in shaping cultural and religious narratives underscores its profound impact on humanity. Today, tidal energy has become known as a resource that can be used over and over again and could help with finding long-term energy options. The steady flow of water is used to make energy by projects like tidal barrages and underwater windmills. But these tools need to find a way to get energy while also protecting fragile marine environments. Seasonal cycles and the role of Earth's tilt. Earth's axial tilt, or obliquity, is the primary driver behind the seasonal cycles that shape life and ecosystems across the planet. At 23.5 degrees, this tilt gives rise to the diverse seasonal patterns experienced in different regions of the globe. These cycles not only influence weather and ecosystems, but have also been central to the development of human cultures and civilizations. The tilt of Earth's axis relative to its orbital plane causes sunlight to strike different parts of the planet at varying angles throughout the year. When the northern hemisphere is tilted toward the sun, it experiences summer, with longer days and more direct sunlight. Conversely, the southern hemisphere experiences winter, marked by shorter days and weaker sunlight. 6 months later, the situation reverses, showcasing the symmetry of Earth's orbital dynamics. This axial tilt results in pronounced differences between the equatorial, temperate, and polar regions. Near the equator, seasonal changes are minimal, with temperatures remaining relatively stable year-round. In contrast, temperate zones experience the full spectrum of seasons, from the warmth of summer to the chill of winter. At the poles, the tilt creates extreme conditions, including months of perpetual daylight or darkness. Seasonal changes are very important to the way environments work. They control when animals migrate, when they breed, and what supplies are available. For example, a lot of different bird species fly long distances to summer places with lots of food. In the same way, plants have evolved to flower and spread their seeds at the same time every season. This helps them stay alive and make more plants. Agriculture, a cornerstone of human civilization, is deeply tied to seasonal cycles. Ancient societies, such as those in Mesopotamia and Egypt, developed calendars based on the annual flooding of rivers, which was driven by seasonal changes. These early calendars allowed for the prediction of planting and harvesting times, fostering the growth of stable agricultural economies. To be clear, Earth's axial tilt is not always the same. It moves back and forth between about 22.1 and 24.5 degrees over long periods of time because of the Moon and other stellar bodies' gravity pull. These changes, which are part of the Milankovitch cycles, affect how strong and where the seasons are. When the tilt is higher, the differences between the seasons are more noticeable. When the tilt is lower, the seasons are warmer. These changes have caused changes in the climate in the past, such as the start and end of ice ages. As Earth's climate continues to change due to human activity, the interplay between seasonal cycles and climate systems becomes increasingly complex. Rising global temperatures can disrupt established seasonal patterns, leading to phenomena such as prolonged heat waves, delayed winters, or erratic rainfall. These changes affect ecosystems and human societies, challenging our ability to adapt. Seasonal cycles have also shaped cultural and spiritual practices throughout history. From solstice celebrations to harvest festivals, human traditions often reflect a deep awareness of the rhythms of nature. Understanding and honoring these cycles has been a way for societies to align with the natural world, fostering a sense of connection and stewardship. These days, technology lets us watch changes in the seasons with a level of accuracy that has never been seen before. Changes in vegetation, snow cover, and the weather are tracked by satellites. This information is very important for handling farmland, water supplies, and getting ready for disasters. These tools help us predict and lessen the effects of natural changes, which makes us more resilient when things change. The Wilson cycle. The Wilson cycle, a geological process spanning hundreds of millions of years, governs the assembly and breakup of supercontinents on Earth. This vast cyclical phenomenon has profound effects on Earth's climate, ocean circulation, and biodiversity, shaping the planet's history in ways that are still being uncovered. Named after Canadian geologist J. Tuzo Wilson, the Wilson cycle describes the repeated formation and fragmentation of supercontinents, driven by plate tectonics. It begins with the rifting of a supercontinent, creating new ocean basins. Over time, these basins expand as tectonic plates diverge. Eventually, the movement reverses, causing the ocean basins to close through subduction, where one plate is forced beneath another. This culminates in the collision of continents, forming a new supercontinent and restarting the cycle. The most recent supercontinent, Pangaea, existed approximately 335 million years ago during the late Paleozoic and early Mesozoic eras. Its breakup gave rise to the continents and oceans we recognize today. Before Pangaea, earlier supercontinents such as Rodinia and Gondwana underwent similar cycles of formation and dispersal. Each iteration of the Wilson cycle has left distinct marks on Earth's geological and biological record. The impact on global climate is among the most notable outcomes of the Wilson cycle. The formation of a supercontinent has the potential to change weather patterns and interfere with the movement of the oceans. As an example, the enormous landmass of Pangaea resulted in harsh temperatures, with desert interiors that were cut off from the ocean's regulating impact. In contrast, ocean currents become more active and climates become milder and more stable as supercontinents split apart, leading to an increase in the number of smaller continents and coastlines. The Wilson cycle also plays a key role in the evolution of life. The breakup of supercontinents creates isolated environments, driving speciation and biodiversity. As continents drift and collide, ecosystems are reshaped, leading to both opportunities and challenges for survival. Mass extinctions, such as the Permian-Triassic extinction event, have been linked to the climatic and geological upheavals caused by these tectonic processes. Subduction zones, where oceanic plates are forced beneath continental plates, are hotspots of geological activity. They generate volcanic arcs, mountain ranges, and deep-sea trenches, contributing to the dynamic nature of Earth's surface. These regions are also critical for recycling Earth's crust, as subducted material melts and resurfaces through volcanic activity. Thanks to today's technology, we can examine the Wilson cycle with a level of precision never seen before. We may learn more about the tectonic plate movement and the factors that drive it through satellite imagery, seismic research, and sophisticated modeling. By using these methods, we may learn more about Earth's geological history and make more accurate predictions about future tectonic events, such as the possible creation of a new supercontinent. The ongoing drift of today's continents suggests that we are in the early stages of a new Wilson cycle. Geologists predict that in 200 to 300 million years, the continents could converge again, forming a supercontinent often referred to as Pangaea Proxima or Amarcia. This future landmass will bring new climatic and ecological challenges, offering a glimpse into the planet's long-term evolution. Mass extinctions and Earth's resilience. Mass extinctions are among the most dramatic events in Earth's history, resetting life on the planet and paving the way for new evolutionary pathways. These catastrophic events, while devastating in the short term, highlight Earth's remarkable resilience and capacity for renewal. Throughout the planet's history, there have been 5 major mass extinctions, collectively known as the Big Five. Each was caused by a unique combination of environmental changes, from volcanic eruptions to asteroid impacts, leading to the loss of 70% or more of Earth's species. Despite the scale of these events, life has rebounded each time, often in ways that reshaped ecosystems and gave rise to new forms of biodiversity. The Ordovician-Silurian extinction, around 443 million years ago, was triggered by a dramatic ice age, which caused sea levels to plummet. Marine ecosystems were particularly hard hit, as many species could not adapt to the rapidly changing conditions. Similarly, the late Devonian extinction, about 375 million years ago, was marked by a series of environmental upheavals, including anoxic, oxygen-deprived events in the oceans that decimated marine life. Perhaps the most infamous extinction event is the Permian-Triassic extinction, often called the Great Dying. Occurring approximately 252 million years ago, it remains the most severe extinction in Earth's history, wiping out an estimated 90% of marine species and 70% of terrestrial species. The causes include massive volcanic eruptions in the Siberian traps, which released vast amounts of greenhouse gases, leading to global warming, ocean acidification, and widespread anoxia. Despite the devastation, the aftermath of this event saw the rise of the first dinosaurs, setting the stage for the Mesozoic era. The Triassic-Jurassic extinction, about 201 million years ago, was similarly transformative. It was driven by intense volcanic activity associated with the breakup of Pangaea. The event cleared ecological niches that allowed dinosaurs to dominate the Earth for the next 135 million years. The Cretaceous-Paleogene (KPG) extinction, 66 million years ago, ended the reign of the dinosaurs. A combination of a massive asteroid impact and extensive volcanic activity caused rapid climatic changes, including a nuclear winter scenario where sunlight was blocked by debris in the atmosphere. The extinction paved the way for mammals to rise, eventually leading to the emergence of humans. These events demonstrate the resiliency of life despite the immense devastation they produced. Each time a species went extinct, its environment had to adjust and develop to make up for it. Take the demise of the dinosaurs as an example. It opened up new ecological niches for mammals, who were able to diversify and thrive. Likewise, many marine, plant, and insect species have survived and even thrived in post-extinction worlds by adapting to new conditions. Scientists now express concern that human actions, rather than natural disasters, might trigger a sixth mass extinction. The rate of biodiversity loss is being accelerated at an unprecedented rate due to factors such as habitat degradation, climate change, pollution, and overexploitation of resources. The current extinction is taking place over hundreds of years, not millennia, like previous ones. Understanding mass extinctions from the past can help us lessen the effects of present natural problems. Scientists can find ways to protect environments and keep biodiversity alive by looking at how life returned from past events. To stop a wide-scale ecological collapse, we need to work together on conservation efforts, environmentally friendly practices, and foreign unity. The Younger Dryas and sudden climate shifts. Around 12,800 years ago, there was a short but intense time of world cooling called the Younger Dryas. This shows how quickly and unexpectedly Earth's climate can change. This event shook up ecosystems and had an effect on early human societies. It also teaches us a lot about how climate changes quickly. Named after the alpine flower Dryas octopetala, which thrived in the cold conditions of the time, the Younger Dryas is one of the most well-documented examples of a sudden climate shift. Before its onset, Earth was transitioning out of the last ice age, with warming temperatures leading to retreating glaciers and expanding ecosystems. However, this progress was abruptly halted, and temperatures plummeted back to near-glacial conditions within a matter of decades. The cause of the Younger Dryas remains a topic of scientific debate, but one leading hypothesis involves the disruption of the North Atlantic Ocean's Thermohaline circulation. As massive ice sheets melted, vast amounts of fresh water flooded into the ocean, particularly from the Laurentide ice sheet in North America. This influx of fresh water reduced the salinity and density of seawater, weakening the ocean currents that transport warm water from the tropics to higher latitudes. The result was a significant cooling effect, particularly in the northern hemisphere. The potential for an alien collision is another striking hypothesis. According to some experts, a comet or asteroid impact could have started many fires that sent soot and dust into the air. This would have blocked the sun and dropped temperatures around the world quickly. A layer of carbon-rich sediment and tiny spherules found at different Younger Dryas sites support this idea. These features are consistent with the debris left over from a high-energy impact. The Younger Dryas profoundly affected ecosystems and early human populations. In many regions, the abrupt cooling led to the expansion of ice sheets and glaciers, altering landscapes and forcing species to adapt or migrate. In Europe and Asia, species that had begun moving northward during the warming period were suddenly pushed back into refuges. Large mammals such as mammoths and saber-toothed cats faced additional pressures, contributing to their eventual extinction. For early human societies, the Younger Dryas posed significant challenges. Archaeological evidence suggests that communities had to adapt quickly to changing conditions, often shifting their subsistence strategies. In the Levant, the cooling period coincides with the Natufian culture, which transitioned from hunter-gathering to early agriculture. Some researchers propose that the environmental stress of the Younger Dryas may have been a catalyst for the development of farming as a means of ensuring food security in the face of unpredictable climates. The Younger Dryas ended as abruptly as it began, with temperatures rebounding around 11,700 years ago. This marked the start of the Holocene epoch, a period of relatively stable climate that has allowed human civilizations to flourish. The rapid transition out of the Younger Dryas may have been driven by the resumption of the Thermohaline circulation, or a gradual reduction in the factors that triggered the cooling. Looking into the Younger Dryas gives us important information about how sudden climate change works. It shows how Earth's systems are linked. Changes in one part, like the amount of fresh water coming in or the makeup of the atmosphere, can have ripple effects on weather and ecosystems around the world. It also shows how important it is to be resilient and adapt, which are lessons that are still very useful as we deal with the problems of climate change today. The carbon cycle. The carbon cycle is the lifeblood of Earth's ecosystems, a fundamental process that drives climate regulation, supports life, and shapes the planet's future. It is the intricate dance of carbon atoms moving through the atmosphere, oceans, land, and living organisms, creating a dynamic equilibrium that has persisted for billions of years. The atmosphere, biosphere, hydrosphere, and geosphere are the four main places where carbon is stored. They are constantly exchanging carbon with each other. Carbon is mostly found in the atmosphere as carbon dioxide, CO2, a greenhouse gas that keeps the Earth's temperature stable. During photosynthesis, plants take in this carbon from the air and turn it into organic molecules that keep the food web going. These plants are then eaten by animals, which moves carbon around the environment. The oceans act as a massive carbon sink, holding more carbon than the atmosphere and biosphere combined. CO2 dissolves in seawater, where it can either remain as dissolved gas or react with water to form bicarbonate and carbonate ions. Marine organisms, such as corals and shellfish, use these ions to build their calcium carbonate shells. When these organisms die, their shells sink to the ocean floor, where they can become sedimentary rock, effectively sequestering carbon for millions of years. The geosphere represents the longest-term reservoir in the carbon cycle. Over geological timescales, processes such as plate tectonics, weathering, and volcanic activity move carbon between the Earth's crust, atmosphere, and oceans. Carbon locked in rocks is gradually released through volcanic eruptions or as fossil fuels are extracted and burned. This slow geological carbon cycle acts as a stabilizing force, helping to balance short-term fluctuations. The natural carbon cycle, on the other hand, has been drastically changed by humans. Carbon dioxide levels in the air have risen by more than 40% since the Industrial Revolution. This is because burning fossil fuels like coal, oil, and natural gas releases huge amounts of carbon dioxide into the air. Cutting down trees for their wood has made this problem worse because fewer plants are able to take in CO2 through photosynthesis. The greenhouse effect has sped up because of these problems, which has caused climate change and global warming. The consequences of this imbalance are already evident. Rising temperatures have triggered feedback loops that amplify carbon release, such as the thawing of permafrost. Permafrost, a layer of frozen soil in Arctic regions, contains vast amounts of organic carbon. As it thaws due to warming temperatures, this carbon is released as CO2 and methane, a potent greenhouse gas, further accelerating climate change. Ocean acidification is another critical issue linked to the disrupted carbon cycle. As oceans absorb more CO2 from the atmosphere, their pH levels decrease, making the water more acidic. This change threatens marine ecosystems, particularly organisms with calcium carbonate shells, such as corals and mollusks. Coral reefs, which support a quarter of all marine species, are especially vulnerable, with bleaching events becoming more frequent and severe. To lessen the effects of a broken carbon cycle, people are working to both cut down on pollution and improve carbon storage. Renewable energy sources like solar and wind can be used instead of fossil fuels. Reforestation projects, on the other hand, try to bring back trees that absorb carbon. New methods such as carbon capture and storage, CCS, try to take CO2 out of the air and either store it underground or use it in manufacturing processes. The role of deep soil carbon in climate regulation. Beneath our feet lies one of Earth's most significant yet underappreciated carbon reservoirs, the deep soil carbon pool. This hidden storehouse plays a pivotal role in regulating the planet's climate, serving as both a carbon sink and, under certain conditions, a carbon source. Understanding the dynamics of deep soil carbon is essential for predicting how Earth's climate will respond to future changes, and for identifying strategies to mitigate global warming. Deep soil carbon refers to organic matter and inorganic carbon compounds stored at depths beyond the reach of typical surface processes, often extending several meters below the ground. Unlike the more active carbon in surface soils, deep soil carbon is relatively stable, with some fractions remaining locked away for thousands or even millions of years. This long-term storage makes it a critical component of the carbon cycle, helping to moderate atmospheric CO2 levels over geological timescales. Plants are the primary entry point for carbon into the soil system. Through photosynthesis, they capture atmospheric CO2 and use it to build organic material. When plants die or shed leaves and roots, this organic matter becomes incorporated into the soil. In deeper layers, roots and microbial activity facilitate the transfer of carbon, where it becomes bound to minerals or encased in aggregates, significantly slowing its decomposition. However, the stability of deep soil carbon is not guaranteed. Changes in land use, climate, and soil management practices can disturb these deep carbon stocks, releasing CO2 into the atmosphere. For instance, deforestation and agriculture often involve tilling, which exposes deeper soil layers to oxygen, accelerating the decomposition of organic matter. Similarly, the thawing of permafrost, a process occurring rapidly in Arctic regions due to rising temperatures, can release large amounts of previously stable carbon, amplifying global warming. Recent studies have highlighted the influence of soil microbiomes on deep carbon dynamics. Microorganisms play a dual role. They help stabilize carbon by incorporating it into durable compounds, but they also break down organic matter, releasing carbon dioxide. Changes in microbial activity due to temperature fluctuations, moisture levels, or nutrient availability can therefore have profound effects on soil carbon storage. One of the most concerning aspects of deep soil carbon dynamics is the potential for positive feedback loops. As global temperatures rise, increased microbial activity and permafrost thaw could release more CO2, which in turn would drive further warming. This cycle could compromise the role of soils as a carbon sink, turning them into a significant carbon source. On the flip side, deep soil carbon also represents an opportunity for climate mitigation. Practices such as regenerative agriculture, agroforestry, and no-till farming can enhance the storage of carbon in soils. By promoting the growth of deep-rooted plants and minimizing soil disturbance, these methods help lock away more carbon at greater depths. Additionally, biochar, carbon-rich material created through the pyrolysis of organic matter, has shown promise in stabilizing soil carbon and enhancing its long-term sequestration potential. Technological advancements are aiding efforts to understand and manage deep soil carbon. Soil cores, remote sensing, and isotopic analyses provide insights into the age, composition, and turnover rates of deep carbon pools. These tools are helping scientists build more accurate models of how soil carbon dynamics interact with broader climate systems, offering a clearer picture of the challenges and opportunities ahead. The deep soil carbon pool is a silent but vital player in Earth's climate story. As we strive to mitigate climate change and build resilience against its impacts, harnessing the potential of this hidden resource could be a game changer. By protecting and enhancing deep soil carbon stores, humanity can tap into one of nature's most powerful tools for securing a stable climate future. The role of Earth's biosphere in climate regulation. The environment, which is made up of all living things on Earth, is very important for keeping the temperature stable. Life on Earth helps keep the balance that ecosystems need to grow by contributing to the cycling of important elements like carbon, nitrogen, and oxygen through a complicated web of interactions. One thing that everyone can see that the environment does is photosynthesis. Carbon dioxide, CO2, from the air is taken in by plants, algae, and some bacteria. They then turn it into organic matter, which releases oxygen. This basic trade not only keeps life going, but it also soaks up carbon, which lowers the amount of warming gases in the air. A lot of carbon is stored in forests, especially tropical jungles like the Amazon. Each year, trees take in billions of tons of CO2. The oceans are another vital component of the biosphere's role in climate regulation. Phytoplankton, microscopic organisms in the oceans, perform photosynthesis on a massive scale. They form the base of the marine food web and play a crucial role in the carbon cycle by sequestering CO2 when they die and sink to the ocean floor. This process, known as the biological pump, transfers carbon from the atmosphere to the deep ocean, where it can remain for centuries or millennia. Through their roles in nutrient cycle, animals also affect how the environment works. For example, animals that graze help keep grassy environments healthy by making plants grow, which absorbs CO2. In marine settings, animals like whales move around and leave behind waste that spreads nutrients that help phytoplankton grow. Many people don't know how important microorganisms are to the biosphere's temperature processes. Soil bacteria break down organic matter, which recycles nutrients and lets warming gases like CO2 and methane escape. This release of carbon is a normal part of the carbon cycle. However, farming and cutting down trees can mess up these bacteria processes, which makes greenhouse gas emissions worse. Nevertheless, there is mounting pressure on the biosphere to maintain its climatic regulation capabilities. Wetlands, forests, and other ecosystems are less able to absorb carbon dioxide due to pollution, habitat loss, and deforestation. An increase in the average global temperature puts more strain on these systems, leading to a vicious cycle that makes climate change even worse. One example is the release of methane from frozen organic matter as a result of permafrost thawing due to rising Arctic temperatures. Oxygenation events in Earth's history. The history of oxygen on Earth is a story of change, life, and progress. The Earth's climate and the ability for complicated life to develop have been shaped by oxygenation events, which are big rises in the amount of oxygen in the atmosphere and oceans. These events were turning points in Earth's past. They changed ecosystems fundamentally and led to big steps forward in development. The first and most significant oxygenation event, known as the Great Oxidation Event, GOE, occurred around 2.4 billion years ago. Before this period, Earth's atmosphere was largely devoid of oxygen, dominated instead by methane, carbon dioxide, and nitrogen. Microbial life thrived in this anoxic world, particularly anaerobic organisms that did not require oxygen for survival. The GOE was triggered by the emergence and proliferation of cyanobacteria, microscopic organisms capable of photosynthesis. These cyanobacteria, also known as blue-green algae, produced oxygen as a byproduct of their metabolic processes. Over millions of years, their activity released enough oxygen to saturate the oceans, gradually escaping into the atmosphere. This accumulation of oxygen marked a profound shift, transforming Earth's environment from a reducing to an oxidizing state. The immediate effects of the GOE were both dramatic and catastrophic. Oxygen, though essential for modern life, was toxic to many anaerobic organisms that had dominated the planet. This led to a mass extinction event, wiping out large portions of the microbial biosphere. However, for organisms that could tolerate or utilize oxygen, the GOE opened up new ecological niches, driving evolutionary innovation and complexity. The rise of oxygen also had profound geological implications. It reacted with abundant iron in the oceans, forming iron oxide deposits that settled on the sea floor. These banded iron formations, BIFs, serve as a geological record of this transformative period. Additionally, oxygen in the atmosphere led to the formation of the ozone layer, shielding the planet from harmful ultraviolet radiation and creating conditions favorable for life to thrive on land. Following the GOE, oxygen levels fluctuated for nearly 2 billion years, remaining relatively low but gradually increasing. It wasn't until the Neoproterozoic era, around 800 million years ago, that oxygen levels rose significantly again. This second oxygenation event, often referred to as the Neoproterozoic oxygenation event, set the stage for the rise of multicellular life. It coincided with the emergence of the Ediacaran biota, the first large and complex organisms, and laid the groundwork for the Cambrian explosion, a period of rapid diversification in life forms. During the Devonian period, about 400 million years ago, the third big event of oxygenation took place. There is a link between this event and plants taking over land. Plants photosynthesized on a huge scale as they spread across countries, adding oxygen to the air. This rise in oxygen levels helped bigger and more complicated animals evolve, including the first mammals that lived on land. Oxygen levels have changed over Earth's past, even though they are very important for life. The frailty of this balance is shown by times when oxygen levels drop, which are often linked to mass extinctions. For instance, the Permian-Triassic extinction event, which was the worst in Earth's history, may have been caused in part by a drop in oxygen levels, as well as changes in the temperature and volcanic activity. Even now, the oxygen cycle is still very important for keeping Earth habitable. The balance between the amount of oxygen that photosynthetic organisms make and the amount that breathing and decay use up is still very delicate. Pollution and cutting down trees are two things that people do that upset this balance. This shows how important it is to protect the ecosystems that keep it going. The role of biodiversity in stabilizing cycles. Earth's robustness is built by biodiversity, which is often overlooked. Not only does the range of life on Earth keep its systems stable, but so does the complex web of relationships between its parts. Biodiversity is a key part of keeping Earth's natural processes stable. It controls the carbon cycle, keeps the soil fertile, and manages water supplies. Ecosystems are composed of countless organisms, each performing specific roles that contribute to broader environmental stability. Plants, for instance, play a crucial role in sequestering carbon dioxide during photosynthesis, reducing greenhouse gases in the atmosphere, and helping to mitigate climate change. Forests act as vast carbon sinks, storing more carbon than they release, which is essential in buffering the carbon cycle. The loss of these ecosystems not only diminishes this capacity, but can also exacerbate carbon emissions, creating feedback loops that accelerate climate change. Microbial life, though often overlooked, is another cornerstone of Earth's stability. Microbes drive critical biochemical processes, such as nitrogen fixation, which makes nitrogen available to plants, and the decomposition of organic material, which recycles nutrients back into ecosystems. Without these unseen workers, the nutrient cycles that sustain plant and animal life would falter, leading to widespread ecological collapse. Biodiversity also contributes to water regulation, with vegetation playing a pivotal role in maintaining the water cycle. Forests and wetlands act as natural sponges, absorbing rainfall and releasing it gradually into rivers and aquifers. This reduces the risk of floods during heavy rains and ensures a steady supply of water during dry periods. Mangroves, for instance, provide coastal protection by stabilizing shorelines and buffering against storm surges, while also serving as breeding grounds for countless marine species. Along with its useful functions, variety makes environments more resilient by acting as a kind of insurance. When things go wrong, like extreme weather, disease outbreaks, or human activities, environments with a lot of different types of life can better handle it and heal. This is because different species can play similar biological roles. If one species goes extinct or decreases in number, others can step in and keep important functions going. This backup is very important for keeping things stable over Earth's cycles, especially when things change quickly in the world. But the loss of variety is a big problem for these processes that keep things stable. Deforestation, ecosystem damage, pollution, and over-exploitation of resources are just some of the things that people do that have sped up the extinction rates to levels that have never been seen before. Each loss not only means the end of a unique species, but also the breakdown of the complex relationships that keep Earth's balance. For instance, the loss of pollinators like bees has huge effects on farming and food security because many crops depend on them to reproduce. Climate change compounds the risks to biodiversity. Rising temperatures, shifting weather patterns, and increasing sea levels disrupt habitats, forcing species to adapt, migrate, or face extinction. Coral reefs, often referred to as the rainforests of the sea, are particularly vulnerable, with warming oceans causing widespread bleaching events that threaten their survival. The loss of coral reefs would not only devastate marine biodiversity, but also disrupt fisheries and the livelihoods of millions of people. It's not enough to just protect individual species. We also need to protect the processes that make Earth livable. Protecting these systems requires important steps like planting more trees, fixing up habitats, and setting up protected areas. International groups like the Convention on Biological Diversity are trying to organize action around the world because they know that losing biodiversity is a problem that affects more than one country. Ecosystem tipping points, crossing the line of no return. Ecosystem tipping points represent critical thresholds beyond which a system undergoes irreversible change. These transitions are driven by interconnected processes within Earth's cycles and are increasingly accelerated by human activity. Understanding these tipping points is essential for anticipating their impacts and preventing catastrophic shifts in climate, biodiversity, and resource availability. One of the most discussed tipping points is the Amazon rainforest's dieback. Often referred to as the lungs of the Earth, the Amazon absorbs vast amounts of CO2 and plays a vital role in regulating global weather patterns. Deforestation, agricultural expansion, and climate change have pushed the rainforest closer to a point where it could shift from a carbon sink to a carbon source. Scientists estimate that if deforestation surpasses 20–25% of its original area, the Amazon could transition into a savanna-like ecosystem. This would drastically reduce its ability to absorb carbon, amplifying global warming and altering regional rainfall patterns. The Arctic ice albedo feedback is another critical tipping point. As Arctic sea ice melts due to rising temperatures, the reflective surface of ice is replaced by darker ocean water, which absorbs more sunlight. This leads to further warming and accelerated ice loss. Once this feedback loop intensifies, it could trigger widespread permafrost thawing, releasing massive amounts of methane, a potent greenhouse gas, into the atmosphere. This domino effect has global implications, raising sea levels and intensifying extreme weather events. Coral reefs, often described as the rainforests of the ocean, are also at risk of crossing a tipping point. Rising ocean temperatures and acidification have caused widespread coral bleaching, with some regions losing more than 50% of their coral cover. If global temperatures rise beyond 1.5 degrees Celsius above pre-industrial levels, many coral ecosystems may face collapse, threatening marine biodiversity and the livelihoods of millions of people who depend on these ecosystems for food and income. The Greenland and West Antarctic ice sheets are additional systems on the brink. These massive ice reserves are melting at an accelerating rate, contributing to global sea level rise. If the melting reaches a critical threshold, it could lead to the complete disintegration of these ice sheets over centuries or millennia. This would raise sea levels by several meters, inundating coastal cities and reshaping the world's coastlines. Ecosystem tipping points are interconnected, meaning a shift in one system can trigger cascading effects in others. For example, the loss of Arctic sea ice can disrupt atmospheric circulation, altering monsoon patterns in Asia and rainfall in the Amazon. This interconnectedness highlights the urgency of addressing environmental degradation holistically, rather than focusing on individual systems in isolation. Preventing ecosystems from crossing tipping points requires proactive measures. Protecting and restoring natural habitats, reducing greenhouse gas emissions, and adopting sustainable resource management practices are essential. Global initiatives like the Paris Agreement and the Convention on Biological Diversity aim to address these challenges by fostering international cooperation and setting ambitious targets for conservation and climate action. Scientific advances are also enhancing our ability to monitor and predict tipping points. Satellite observations, ecological modeling, and real-time data collection provide critical insights into ecosystem health and resilience. These tools enable early warning systems, helping policymakers and communities take timely action to prevent irreversible changes. The interplay between soil health and climate stability. The Earth beneath our feet is one of the most undervalued but vital resources on Earth. In addition to anchoring plants, storing water, and acting as a dynamic carbon sink, this microscopic layer of organic materials and minerals is an essential component of Earth's biosphere. Agricultural output, water cycles, and world temperatures are all impacted by soil health, which is in turn affected by climatic stability. Healthy soils act as a major reservoir for carbon. Through a process known as carbon sequestration, soils absorb and store carbon dioxide from the atmosphere, mitigating climate change. Plants play a pivotal role in this cycle by capturing carbon dioxide during photosynthesis and transferring it to the soil through their roots. Microorganisms and fungi then break down organic matter, incorporating carbon into the soil. This process not only reduces atmospheric CO2 levels, but also enhances soil fertility. But changes in land use and farming methods that aren't sustainable risk this delicate balance. Soil is broken down by cutting down trees, overgrazing animals, and intense gardening, which releases carbon back into the air. For example, tilling, which is a popular gardening method, changes the structure of the soil and speeds up the breakdown of organic matter, which causes more carbon to be released into the air. This damage adds to the greenhouse effect, which makes global warming worse. Soil erosion compounds the problem, removing nutrient-rich topsoil and reducing the land's capacity to support vegetation. Without plant cover, the exposed soil is more vulnerable to wind and water erosion, creating a vicious cycle of land degradation and desertification. Regions like the Sahel in Africa vividly illustrate the consequences of soil erosion, where overexploitation of the land has led to barren landscapes and diminished agricultural yields. Beyond its role as a carbon sink, soil regulates water cycles and buffers against extreme weather events. Healthy soils have a spongy structure that absorbs and retains water, reducing the risk of flooding during heavy rains and maintaining water availability during droughts. Degraded soils, by contrast, lose their capacity to hold water, increasing the frequency and severity of these extremes. This has significant implications for food security, as crops depend on consistent water availability. Microbial life in the soil is also very important for keeping ecosystems stable. Fungi and bacteria help the cycle of nutrients by breaking down organic matter into forms that plants can use. As a biological engine, this deep environment helps plants grow, which in turn supports whole food webs. Pollution, usage of chemical fertilizers, and habitat loss all lead to a loss of biodiversity in the soil. This threatens these important processes and makes ecosystems even less stable. Restoring the health of the land is a strong way to fight climate change and encourage longevity. No-till farming, cover crops, and agroforestry are all methods that protect the structure of the soil and make it better at storing carbon. Reforestation and afforestation projects also help restore soil by stopping it from washing away and adding organic matter. Also, progress in studying the soil microbiome is revealing fresh methods to use bacteria power for long-lasting farming. Permafrost thaw and methane release. People often think of the Arctic as frozen and dead, but permafrost is one of the most important things that keeps the Earth's temperature stable. This layer of dirt and organic matter has been frozen solid for thousands of years, storing huge amounts of carbon and methane below its icy surface. But as temps rise around the world, this old barrier is starting to melt. This could cause effects that speed up climate change by a huge amount. Permafrost covers approximately 24% of the Northern Hemisphere's land area, primarily in Siberia, Alaska, and Canada. Within this frozen ground lies an enormous store of organic matter accumulated over thousands of years from decayed plants and animals. When permafrost remains frozen, this organic carbon is inert, effectively locked away from the atmosphere. However, thawing permafrost exposes this material to microbial decomposition, which releases carbon dioxide and methane into the atmosphere. Methane, although less abundant than carbon dioxide, is a far more potent greenhouse gas. Over a 20-year period, Methane traps about 80 times more heat in the atmosphere than carbon dioxide. This amplifies the warming effect, creating a feedback loop. As permafrost thaws, more methane is released, which leads to further warming, causing even more permafrost to thaw. This self-reinforcing cycle is one of the most alarming aspects of climate change. Thawing permafrost also has direct impacts on ecosystems and human infrastructure. As the ground softens, it destabilizes buildings, roads, and pipelines in Arctic regions, leading to costly damages. Entire communities are at risk of displacement as the landscape transforms, with sinking ground and expanding lakes reshaping once frozen terrains. The changes also affect wildlife, as species adapted to cold environments face habitat loss and competition from invasive species moving northward. Scientists estimate that permafrost contains roughly 500 billion metric tons of organic carbon, nearly double the amount currently in the atmosphere. Even a partial release of this carbon could push global temperatures beyond critical thresholds, exacerbating the effects of climate change. Recent studies have observed methane bubbling up from Arctic lakes and newly formed wetlands, visible signs of the permafrost's response to warming temperatures. Permafrost warming has effects that go beyond the Arctic. The release of methane from permafrost adds to global warming, which in turn makes the effects of climate change worse around the world. The effects of more greenhouse gas pollution are linked to things like rising sea levels, extreme weather, and problems with farming systems. Another less well-known risk is the release of germs that have been buried in permafrost for a long time. As these germs thaw, they might come back to life and threaten the health of people and animals. The problem of permafrost thaw needs to be solved quickly and in new ways. The most important thing to do is cut down on greenhouse gas pollution, which can slow down global warming and slow down the melting of permafrost. But new methods are being looked into, like direct air capture of carbon dioxide and methane, to lessen the effects. Some experts are also looking into geoengineering techniques, like making surfaces that bounce light to keep Arctic areas from absorbing too much heat. However, these ideas are still controversial. Monitoring and understanding permafrost dynamics is equally essential. Satellite observations, ground-based measurements, and computer models provide valuable data on permafrost changes and methane emissions. These tools help scientists predict future scenarios and inform policy decisions aimed at mitigating the impacts of permafrost thaw. The role of permafrost microbes in Earth's evolution and climate. Permafrost contains vast quantities of dormant microbes, including bacteria, archaea, and viruses. Encased in ice for millennia, these microorganisms remain viable, waiting for the right conditions to reawaken. As global temperatures rise and permafrost thaws, these ancient life forms are released into the environment, re-entering the global ecosystem. This microbial awakening has implications for biogeochemical cycles, as their metabolic activities release carbon dioxide, CO2, and methane, CH4, two potent greenhouse gases, into the atmosphere. One interesting thing about permafrost bacteria is how tough and flexible they are. Some are methanogens, which are specialized archaea that do well when there isn't enough oxygen and make methane when they break down organic matter. Because these methanogens are directly involved in the feedback process of global warming. When permafrost melts and releases more organic matter, microbial activity rises, making even more greenhouse gases that speed up warming. These bacteria not only change the temperature, but they also provide a unique look into Earth's evolutionary past. A lot of these species are very old and come from lines that haven't changed much in tens of thousands of years. Their genes are like a living library. They hold information about the world in the past and the ways that living things were able to adapt to harsh circumstances. Bringing back frozen bacteria is not risk-free though. When permafrost melts, it may bring out old pathogens that could harm current environments or even people's health. For instance, anthrax attacks in Siberia have been linked to the melting of permafrost, which let out spores from infected animals that had been dead for a long time. These events show how changes in the environment, the action of microbes, and public health are all linked. The study of permafrost microbes is a growing field, with researchers using advanced techniques such as metagenomics to analyze the genetic composition of these ancient communities. By sequencing DNA directly from permafrost samples, scientists can identify microbial species, reconstruct their metabolic pathways, and model their potential impact on climate dynamics. This information is critical for refining predictions about the pace and consequences of permafrost thaw in a warming world. Earth's cryosphere and its melting trends. The cryosphere, which includes glaciers, ice fields, permafrost, and sea ice, is a very important part of keeping the temperature around the world stable. These icy regions aren't just leftovers from ice ages. They also change the weather, sea levels, and temperature. Still, the cryosphere is getting smaller at a very fast rate, which will have huge effects on the Earth. One of the most obvious effects of losing the cryosphere is that the sea level is going up. Greenland and Antarctic melting glaciers and ice fields add a lot of water to the oceans, which raises the sea level. According to current figures, the world's sea levels could rise by about 7 meters, 23 feet, if all of Greenland's ice melted. This would flood coastal towns and force millions of people to move. Satellite data shows that the rate of ice loss has been steadily increasing over the last few decades, so this process is already underway. Arctic sea ice is an essential part of the cryosphere. When sea ice melts, it doesn't directly raise sea level like mountains do, but it is a very important part of keeping the climate stable. The bright, reflective surface of ice helps block sunshine, which keeps the polar areas cooler. Through a process called ice albedo feedback, as Arctic sea ice melts, the darker water that is left behind soaks up more heat. This makes global warming worse. Around the world, glaciers are also melting. The Himalayas have famous glaciers that feed major rivers like the Ganges, the Indus, and the Yangtze. These rivers bring life to billions of people, but when it's dry, glaciers melt and the rivers move less, which risks water supplies and farming. Threats to ecology, tourists, and local economies can be seen in the Andes and the Alps. Trends in melting in the cryosphere also mess up communities in the ocean. Adding fresh water from glaciers and ice fields changes the temperature and salinity of the oceans, which could slow down the global thermohaline circulation. This can cause big changes in the weather, like storms getting stronger, droughts lasting longer, and rainfall systems changing. Desertification and shifting ecosystems. People often imagine deserts as areas that don't change, but they are actually living environments that grow and shrink over time. One of the biggest problems Earth's environments and people have to deal with is desertification, the process by which rich land turns into desert. This event, which is caused by both natural and human causes, has huge effects on world climate systems, crops, and biodiversity. Desertification is primarily caused by changes in climate and unsustainable land use. Prolonged periods of drought, rising temperatures, and shifting precipitation patterns can strip land of its ability to support vegetation, initiating the slow encroachment of desert conditions. Human activities such as deforestation, overgrazing, and poor agricultural practices exacerbate this process, weakening soil structures and accelerating erosion. The Sahel region of Africa, bordering the southern edge of the Sahara Desert, provides a striking example of how desertification affects ecosystems and human communities. Over the past century, the Sahel has experienced fluctuating rainfall patterns that have pushed the region to the brink of environmental collapse. Prolonged droughts in the 20th century led to widespread crop failures, famine, and displacement of millions of people, illustrating the human toll of desertification. Desertification changes environments and lowers biodiversity, which upsets ecosystems. Native plants and animals that depend on certain conditions often can't change or move when rich land turns into bare land. Losing plants speeds up desertification even more by removing root systems that keep the earth stable and moist, causing a cycle of worsening conditions. The interplay between desertification and climate change magnifies its impact. Degraded lands release stored carbon into the atmosphere, contributing to the greenhouse effect. Simultaneously, rising global temperatures and shifting weather patterns exacerbate arid conditions, increasing the likelihood of further land degradation. These intertwined processes create a vicious cycle, linking desertification to global climate instability. But deserts are also very important to the balance of life on Earth. Nutrients are carried across continents and seas by dust storms that start in deserts like the Sahara. For instance, Saharan dust gives the Amazon rainforest important iron and phosphorus, which helps one of the world's most varied environments. This paradox shows how complicated desertification is, since changes in deserts can have effects on ecosystems far away. Efforts to combat desertification are gaining momentum as the global community recognizes its far-reaching consequences. Sustainable land management practices, reforestation, and the rehabilitation of degraded lands are critical strategies. The Great Green Wall Initiative in Africa is a notable example. This ambitious project aims to create a mosaic of restored landscapes across the Sahel to halt desert expansion, improve livelihoods, and enhance biodiversity. New technologies are also helping to slow down the process of desertification. Scientists can watch land degradation happen in real time using satellite images and advanced modeling. This lets them find places that are at risk and see how well different ways of stopping it are working. Agricultural production can also be kept up in dry areas with the help of sustainable watering methods and crops that don't die from drought. Addressing desertification requires a global effort, as its effects transcend national borders. International agreements, such as the United Nations Convention to Combat Desertification, UNCCD, provide a framework for cooperation, ensuring that resources and knowledge are shared to tackle this challenge collectively. These initiatives emphasize the importance of integrating local and indigenous knowledge with scientific approaches to create effective and sustainable solutions. Ancient climatic catastrophes. Throughout Earth's past, natural disasters have repeatedly changed the course of life, leaving destruction in their wake and making room for fresh starts. These past disasters, which were often caused by natural events, show how unstable the planet is and how strong life is when things go wrong. Understanding these events is very important for understanding how life has changed to adjust to Earth's changing environment and how people might deal with problems in the future. When Mount Toba erupted about 74,000 years ago, it was one of the worst weather events in recorded history. In what is now Indonesia, this supervolcano erupted about 2,800 cubic kilometers of volcanic material into the air, which is a lot more than current earthquakes like the one at Mount Pinatubo in 1991. The volcanic winter that followed, which was caused by sulfur clouds bouncing sunlight away from the Earth, most likely caused a big drop in temperatures around the world. This cooling, along with widespread crop fails and habitat damage, slowed down human development and lowered the world's population to a few thousand people. This time of great poverty changed the genetic diversity of modern humans, showing how much weather events affect our species. Similarly, the Younger Dryas period, a sudden cooling event approximately 12,800 years ago, disrupted ecosystems and human settlements across the globe. While the exact cause remains debated, theories suggest it was triggered by the collapse of the Laurentide ice sheet, which released massive amounts of fresh water into the North Atlantic. This influx disrupted the Thermohaline circulation, leading to abrupt climate changes. For early humans, this meant harsher conditions, forcing nomadic groups to adapt their subsistence strategies and likely accelerating the development of agriculture as communities sought more stable food sources. Volcanic winters have also left their mark on recorded history. The eruption of Mount Tambora in 1815, the largest volcanic event in the last 2,000 years, plunged the world into a year without a summer. Ash and aerosols in the atmosphere cause global temperatures to drop by as much as 3 degrees Celsius, leading to widespread crop failures, famine, and disease outbreaks. Europe, still recovering from the Napoleonic Wars, was particularly hard hit, with grain shortages causing social unrest. This event underscored the interconnectedness of climate and human society, as environmental disruptions reverberated through economies and political systems. The Earth's temperature has been changed by things that happened in space. Most people have heard of the Chicxulub crater, which was made by an asteroid impact 66 million years ago in what is now Mexico. A huge amount of dust and aerosols were released by this terrible event. These blocked sunshine and made the temperature drop dramatically. The resulting mass extinction killed off about 75% of Earth's species, including the dinosaurs that weren't birds. This made way for mammals, and later humans, to take over the world. This event is a stark warning of how aliens can change the climate of Earth and change the direction of development. Climatic catastrophes are not limited to cooling events. Episodes of extreme warming, such as the Paleocene-Eocene thermal maximum, PETM, approximately 56 million years ago, reveal the other side of Earth's climatic volatility. During the PETM, massive releases of carbon dioxide and methane, possibly from volcanic activity, or the destabilization of methane clathrates, caused global temperatures to rise by 5–8 degrees Celsius. This rapid warming led to the extinction of many marine species and forced terrestrial organisms to migrate toward cooler regions. The parallels between the PETM and modern climate change underscore the importance of understanding ancient warming events to predict and mitigate future impacts. Disasters caused by climate change are tragic, but they also show how resilient life is on our planet. In the aftermath of each catastrophe, ecosystems gradually bounced back, frequently with a plethora of new species appearing and a boost to biodiversity. All of this shows how life can adapt and how ecosystems may recover from major disruptions. Human activity and artificial cycles. The natural cycles that have controlled Earth for billions of years are becoming more and more disturbed as the impact of humans on the planet increases. Artificial cycles, brought about by human activity, are new patterns of energy, matter, and climate change that have far-reaching effects on Earth's natural systems. The ecosystem is changing due to human activity, which is disrupting Earth's complex cycles in ways like urban heat islands and worldwide deforestation. Cities with heat islands, UHIs, are one of the most obvious examples of man-made cycles. In cities with lots of people, concrete, asphalt, and other man-made materials soak up and hold on to heat, making cities much warmer than their country settings. This localized warming not only makes it more expensive to cool down, but it also makes health problems worse during heat waves. UHIs also change local weather trends by making storms stronger and stopping air currents from moving. These changes have caused ripple effects that show how settings that people have made can create feedback loops that make their effects stronger on a local and regional level. Deforestation, another major human activity, disrupts the water cycle and carbon cycle on a global scale. Forests act as critical carbon sinks, absorbing large quantities of carbon dioxide and releasing oxygen. When forests are cleared, this balance is disrupted, releasing stored carbon into the atmosphere and contributing to global warming. Additionally, the loss of vegetation reduces transpiration, the process by which plants release water vapor into the atmosphere, leading to changes in local precipitation patterns and increased risks of drought. These disruptions are particularly pronounced in tropical rainforests like the Amazon, where deforestation has pushed some regions dangerously close to a tipping point, beyond which the ecosystem may not recover. Agriculture, particularly industrial farming, is another human activity that creates artificial cycles. The widespread use of fertilizers, which introduce large amounts of nitrogen and phosphorus into the environment, has led to nutrient cycles that far exceed natural levels. These excess nutrients often end up in waterways, causing algal blooms and dead zones, where oxygen levels are too low to support marine life. Such disruptions to the nitrogen cycle not only affect aquatic ecosystems, but also have cascading effects on biodiversity and food security. As a result of people, burning fossil fuels has caused one of the most critical changes to the carbon cycle. By digging up and burning off old carbon stores, people have released huge amounts of carbon dioxide back into the air at a rate that has never been seen before. This has sped up the greenhouse effect, which is raising temperatures around the world. The effects of climate change, such as rising sea levels and more extreme weather events, show how man-made processes can change Earth's natural systems in basic ways. Urbanization and infrastructure development also create artificial water cycles. By channeling rivers, constructing dams, and draining wetlands, humans have altered the natural flow of water across landscapes. These interventions can reduce groundwater recharge, increase flooding risks, and disrupt ecosystems that rely on consistent water availability. For example, the construction of large dams often leads to the displacement of communities, changes in sediment flow, and the loss of habitats for aquatic species. Beyond the physical environment, human activity has introduced artificial cycles of waste and pollution. The production of non-biodegradable materials like plastics has created long-lasting environmental legacies. Plastics can take hundreds to thousands of years to degrade, and their accumulation in oceans and terrestrial environments disrupts ecosystems and harms wildlife. Microplastics, tiny fragments that result from the breakdown of larger plastics, have been found in nearly every corner of the globe, including remote polar regions and deep ocean trenches. Even though manufactured cycles usually have bad effects, more and more people are realizing that we need to lessen those effects. Some of the things that are being done to restore balance are sustainable urban planning, replanting projects, and green farming methods. Humanity can work to balance its activities with Earth's natural systems by planning towns with green areas, using less fossil fuels, and switching to circular economies that make the least amount of trash possible. The impact of human-induced feedback loops. People have created feedback loops that make the effects of climate change worse and mess up Earth's natural processes. These cycles that keep going because of greenhouse gas releases, changes in land use, and ecosystem loss have big effects on the security of the whole world. The loop between Arctic ice and sunlight is a well-known example. Snow and ice reflect sunshine, which helps keep the Earth cool. But as temperatures rise around the world, the Arctic ice melts, revealing darker ocean water that soaks up more heat. This faster warming is caused by more absorption, which in turn causes even more ice to melt. This creates a vicious loop that raises sea levels and messes up weather trends around the world. Deforestation is another driver of human-induced feedback loops. When forests are cleared, they release stored carbon dioxide into the atmosphere, intensifying the greenhouse effect. Additionally, the loss of vegetation reduces the planet's ability to absorb CO2, exacerbating the warming process. Tropical rainforests, often called the lungs of the Earth, are particularly vulnerable. Their degradation could turn them from carbon sinks into carbon sources, accelerating climate change. Ocean acidification is another effect that has effects that keep happening. The pH level of seas drops as they take in more CO2, which makes the water more acidic. Marine habitats are in danger because of this change, especially coral reefs and creatures that build shells, which are very important for biodiversity. Losing these environments can mess up food chains and make the oceans less able to store carbon, which makes climate change worse. Urban heat islands, UHIs, illustrate how human-made environments can create localized feedback loops. Cities, with their abundance of concrete, asphalt, and steel, retain heat, raising temperatures compared to surrounding rural areas. Higher urban temperatures increase energy demand for cooling, leading to more fossil fuel consumption and higher greenhouse gas emissions, which in turn exacerbate the warming effect. Heat waves and urban heat islands. Heat waves, which are long times of unusually high temperatures, are one of the clearest and worst signs of climate change. The world over, their number, strength, and length have been growing, which is very bad for environments, infrastructure, and people's health. This problem is even worse in cities, where something called urban heat islands, UHIs, makes the effects of heat waves stronger by causing hotspots of high heat. Heat waves occur when high-pressure systems trap warm air close to the ground, preventing it from dissipating. This atmospheric stagnation allows temperatures to climb for days or even weeks, often surpassing the natural coping thresholds of organisms and infrastructure. Historically, heat waves have been devastating. For example, the 2003 European heatwave claimed over 70,000 lives, underscoring their deadly potential. However, in the context of climate change, these events are becoming increasingly severe. Rising temperatures around the world are a main cause of heat waves that get worse. Baseline temperatures rise as more greenhouse gases are released into the atmosphere. This makes heat waves hotter and last longer. To make things even worse, hot air can hold more water, creating what are called humid heat waves, which make it harder for the body to cool itself through sweating. Urban areas are particularly vulnerable to heat waves due to the UHI effect. Cities, with their dense concentrations of buildings, asphalt and concrete, absorb and retain heat far more effectively than natural landscapes. This causes urban areas to experience temperatures several degrees higher than their rural surroundings, especially at night when the heat stored in infrastructure is slowly released. The UHI effect makes heat waves more dangerous, especially for people living in cities. Certain groups, like the old, young children, and people who already have health problems, are more likely to get heat-related diseases like heat exhaustion and heat stroke. Using more air cooling can also put a lot of stress on power lines, which can cause blackouts and make the risks even higher. The environmental impact of heat waves extends beyond human health. Prolonged high temperatures can weaken or kill vegetation, reduce soil moisture, and increase the risk of wildfires. Urban heat islands worsen this situation by creating thermal stress zones where plant life struggles to survive. The loss of vegetation further reduces shading and evaporative cooling, perpetuating the cycle of rising temperatures. Heat waves have big effects on the economy. Using more energy for cooling systems puts a strain on infrastructure and makes electricity bills go up. In the worst cases, roads, train lines and power lines that have been damaged by heat need expensive fixes. Aside from that, industries that rely on outdoor activities, like building and agriculture, lose work and health risks during long heat waves. Mitigating the effects of heat waves and urban heat islands requires proactive strategies. Urban planning can play a pivotal role in reducing UHI intensity. Implementing green roofs, increasing tree canopy cover, and using reflective or lighter-colored materials for buildings and pavements can help lower urban temperatures. For instance, cities like Singapore and Los Angeles have adopted extensive greening initiatives and cool pavement programs to combat urban heat. Public health measures are also critical. Early warning systems and heat action plans can provide communities with timely information about impending heat waves, allowing residents to take protective measures. Cooling centers, hydration stations, and public awareness campaigns are essential for reducing heat-related illnesses and fatalities, particularly among vulnerable populations. To lower the long-term risks of heat waves, it is important to deal with the reasons of climate change on a bigger scale. Cutting down on greenhouse gas pollution by using more renewable energy, saving energy, and planting trees can help keep temperatures stable and make future heat waves less intense. Forest fires and the feedback loop of destruction. Forest fires, which are also sometimes called wildfires, are natural events that have a big impact on ecosystems. But because these fires are happening more often and with more force, they are no longer signs of renewal but of natural damage. Forest fires are now part of a dangerous feedback loop that makes climate change worse and risks species. This loop is caused by things like rising global temperatures, long droughts, and human activities. In their natural context, forest fires are essential for certain ecosystems. Fires clear dead vegetation, release nutrients into the soil, and stimulate the germination of fire-adapted plants. For example, the serotinous cones of some pine species only release seeds under the intense heat of a fire, ensuring regeneration. However, when fires become too frequent or too intense, they surpass the threshold of ecological benefit, transforming into agents of devastation. Climate change caused by humans and bad land management are the main reasons why wildfires are getting worse today. As temperatures rise, plants dry out and become fuel that is very easy to ignite. Long droughts, which are another effect of climate change, make this problem worse by making it easy for fires to start and spread quickly. Lightning hits, which can happen naturally, are more likely to start fires in these dry places. Human actions like cutting down trees, burning crops, and setting things on fire by accident make the problem worse. It is very important to worry about the feedback process that forest fires and climate change are creating. When woods burn, they release huge amounts of carbon dioxide into the air, which adds to the greenhouse effect. Loss of greenery also lowers the Earth's ability to absorb CO2, which makes warming trends even stronger. This never-ending circle speeds up climate change and makes future fires more likely, a destructive loop that keeps going and going. The impacts of forest fires extend beyond their immediate environmental consequences. Smoke and particulate matter released during fires pose severe health risks, particularly for vulnerable populations such as children, the elderly, and those with respiratory conditions. Wildfire smoke can travel thousands of kilometers, affecting air quality in distant regions and contributing to public health crises. Biodiversity suffers immensely in the wake of wildfires. Ecosystems that have evolved to tolerate occasional fires are now facing unprecedented challenges. Intense fires destroy habitats, disrupt food chains, and push species to the brink of extinction. For instance, Australia's 2019-2020 bushfire season, known as the Black Summer, destroyed an estimated 18.6 million hectares of land and killed or displaced nearly 3 billion animals, including iconic species like koalas and kangaroos. When it comes to the economy, flames have huge costs. Local and national budgets can get tight because of the cost of fighting fires, the loss of trees, and the damage to infrastructure. As beautiful landscapes are turned into burned-out wastelands, areas that rely on tourism also see their income drop. Also, communities often have long-term effects, like being forced to move or losing their way of making a living, especially in rural and forest-dependent areas. Efforts to mitigate the impact of forest fires must address both prevention and adaptation. Proactive measures such as controlled burns and forest thinning can help reduce the buildup of flammable vegetation, lowering the risk of catastrophic fires. Early warning systems, satellite monitoring, and predictive modeling are critical for detecting and managing fires before they spiral out of control. For example, NASA's Earth Observing System provides real-time data on global fire activity, enabling rapid response efforts. Restoration of burned areas is equally important. Reforestation projects, soil stabilization techniques, and the introduction of fire-resistant plant species can aid in ecosystem recovery. Community engagement and education are vital components of these efforts, empowering local populations to adopt sustainable land use practices and reduce fire risks. Taking action on climate change is still the best long-term way to lower the volume of wildfires around the world. To break the fire-climate feedback circle, it is important to switch to renewable energy sources, use carbon capture tools, and support sustainable farming. Anthropogenic noise and its impact on Earth's cycles. Anthropogenic noise, which includes sounds made by people in cities, factories, traffic, and resource extraction, has spread through the natural world. This noise pollution not only changes how living things act, but it also changes the Earth's natural processes in small ways. A huge number of species' life stages are thrown off by noise pollution. Animals like birds, sea animals, and amphibians that use sound to communicate, find their way or mate, are more likely to get stressed out and change how they act when they are in noisy places. For instance, many bird geos change the frequency of their songs when they live in cities to block out the low-frequency hum of traffic, which can make it harder for them to communicate. Sonar, ship engines, and building work done underwater make noise in marine environments that makes it hard for whales and dolphins to find their way by echolocating. Beyond individual species, noise pollution has cascading effects on ecosystems. Disrupted communication and stress responses can reduce reproductive success, alter predator-prey dynamics, and lead to population declines. These changes in turn impact broader ecological interactions such as nutrient cycling, seed dispersal, and food web stability, creating ripple effects across Earth's systems. Loud noise from people and machines in water can mess up natural cycles like fish breeding and sea animals migrating. Coral reefs are especially at risk because they depend on certain sounds to draw young fish and larvae. These sounds are hidden by too much noise, which makes it harder for young creatures to join the environment and threatens its long-term health. Noise also impacts Earth's physical processes. For instance, seismic surveys used in oil and gas exploration generate powerful sound waves that penetrate the sea floor, affecting sediment stability and altering habitats for benthic organisms. On land, vibrations from heavy machinery and transportation can compact soil, disrupt root growth, and affect groundwater flow, altering both ecological and geological cycles. No one is safe from the effects of noise pollution. High noise levels that last for a long time have been linked to problems sleeping, heart problems, and memory loss. Circadian rhythms are important for keeping cellular balance, and these effects on health are part of a bigger problem with them. Noise pollution can make social and economic problems worse because it causes stress over time. This is because communities that are already struggling often have to deal with more noise from traffic and factories. More and more people are working to reduce noise pollution. With more green areas and noise-absorbing materials, urban planners are making towns quieter. At the same time, tougher rules are lowering the noise levels in factories and on the water. New transportation technologies like electric cars and ship engines that are quieter could also help keep noise levels down. It is very important to keep the fragile balance of Earth's cycles and promote peace between people and nature through these actions. The role of deep ocean currents in Earth's future. The Atlantic Meridional Overturning Circulation, AMOC, a crucial component of the Thermohaline system, plays a central role in regulating Earth's climate. The AMOC transports warm water from the equator to the North Atlantic, where it releases heat into the atmosphere, helping to keep Europe and parts of North America temperate. However, studies indicate that the AMOC has been weakening due to increased freshwater input from melting glaciers in Greenland and the Arctic. This fresh water dilutes the salty surface water, reducing its density and hindering its ability to sink, thereby disrupting the entire circulation. If the AMOC gets weaker or falls apart, it could have very bad effects. Without this important system for moving heat, places like Europe could get very cold, even though the rest of the world is getting warmer. This strange event could throw off weather trends, making winters harsher, droughts last longer, and storms stronger. Disrupting deep ocean currents could also change how nutrients are distributed in the ocean, which would have an impact on fishing and the marine environment as a whole. The Southern Ocean also plays a significant role in Earth's deep ocean currents. Cold, dense water forms near Antarctica and flows into the abyssal depths, driving the global circulation from the southern hemisphere. The stability of this system is similarly threatened by polar ice melt. As Antarctic ice shelves collapse and fresh water enters the ocean, the balance between temperature and salinity is disrupted. This could slow the formation of deep water and weaken the overall circulation, amplifying global climate effects. A less well-known effect of disturbed deep ocean currents is how they affect carbon storage. Assuming over a third of human-generated carbon dioxide emissions, the seas function as a huge sink. Carbon-rich water carried by deep ocean currents reaches the ocean floor where it may remain trapped for millennia. A slowing down in these currents might lower the ocean's capacity to absorb carbon dioxide, therefore aggravating the greenhouse effect and hastening global warming. Moreover, the disturbance of abyssal currents may cause methane hydrates, great concentrations of methane caught in the bottom sediments, to be unstable. Should deep ocean currents diminish, these areas may warm and maybe spew significant amounts of methane, a strong greenhouse gas, into the atmosphere. This feedback loop might further aggravate global warming and lead to an impossible cycle to reverse. The effects of disrupted deep ocean currents would not be confined to the oceans. Coastal communities could face rising sea levels and increased flooding as polar ice melts and ocean circulation changes. Coral reefs, already under stress from warming waters, could suffer further as nutrient flows are altered, threatening biodiversity and the livelihoods of millions who depend on marine resources. Asteroid impacts and long-term consequences. Though infrequent, asteroid impacts have significantly changed the history of Earth and might upset its cycles going forward. Not only are these cosmic collisions reminders of the turbulent beginnings of the solar system, but they also act as agents of major environmental and biological transformation. Understanding the background and possible effects of asteroid strikes helps us to better equip ourselves for and reduce future hazards. Throughout Earth's history, asteroid impacts have played a dual role as both destructive forces and agents of transformation. The most famous example is the Chicxulub impact, which struck the Yucatan Peninsula around 66 million years ago. This event, caused by a 10-kilometer-wide asteroid, triggered a mass extinction that wiped out nearly 75% of all species, including the non-avian dinosaurs. The impact released energy equivalent to billions of atomic bombs, creating a crater over 150 kilometers wide and ejecting vast amounts of dust and aerosols into the atmosphere. This debris blocked sunlight for months or years, leading to a nuclear winter scenario that disrupted Earth's climate and ecosystems. The environmental effects of such impacts are multifaceted. In addition to the initial blast and thermal radiation, asteroid collisions generate massive tsunamis, wildfires, and shockwaves. The ejected material can trigger widespread cooling by reflecting sunlight, a phenomenon known as impact winter. Over time, the release of carbon dioxide and other greenhouse gases from vaporized rocks can lead to long-term warming, creating a feedback loop that further destabilizes Earth's climate. Impacts also have geological consequences. The force of a collision can reshape landscapes, create mountain ranges, and form impact craters that later become lakes or basins. These features often serve as reservoirs for biodiversity, evolving into unique ecosystems over millions of years. Some scientists even hypothesize that asteroid impacts played a role in delivering water and organic compounds to early Earth, setting the stage for the development of life. The potential for future asteroid impacts remains a significant concern. Near-Earth objects, NEOs, asteroids and comets whose orbits bring them close to Earth, pose varying levels of risk depending on their size, composition, and trajectory. NASA and other space agencies have identified thousands of NEOs, but many smaller objects remain undetected. While smaller asteroids may burn up in the atmosphere or cause localized damage, larger ones could have catastrophic global effects. Scientists have come up with ways to find and move asteroids in order to deal with this threat. Observatories on the ground, like the Pan-STARRS and Catalina Sky Survey, are always looking up at the sky for possible asteroids that could hit Earth. Space cameras such as NASA's NEOWISE make observations that add to Earth's observations, making it easier to track NEOs. Early discovery is very important because it gives people more time to come up with and use ways to stop the problem. The kinetic impactor technique is a potential way to move an object. It involves sending a spacecraft to hit an asteroid and change its path. In 2022, NASA's Double Asteroid Redirection Test, DART mission, changed the path of the asteroid moonlet. Dimorphos to show that this method worked. This major achievement showed that people are able to change the paths of possibly dangerous rocks. Scientists are also looking into other methods besides redirection. such as gravity tractors, which use the gravitational pull of a ship to slowly push an asteroid off course. Using focused solar energy to turn some of the asteroid's surface into a jet of gas that changes its direction is another way to do it. Even though these methods are still being worked on, they show how important it is for countries to work together and come up with new ideas for global defense. The societal implications of an asteroid impact are as significant as the physical damage. A large-scale impact could disrupt global food supplies, cause economic collapse, and strain emergency response systems. Simulations and preparedness exercises, such as NASA's planetary defense conferences, aim to improve global readiness by simulating impact scenarios and developing coordinated response plans. The precession of the equinoxes. The precession of the equinoxes, which is also known as the Great Year, is a long-lasting trend that changes Earth's position in space over thousands of years. This event, which is caused by the Sun, the Moon, and Earth's gravitational pull on each other, has a domino effect on Earth's weather and long-term cosmic trends. On a human timescale, the precession is not noticeable, but it is an important part of Earth's natural patterns that have effects on history, climate, and society. Precession occurs because Earth is not a perfect sphere. Its equatorial bulge, combined with gravitational forces from the Moon and the Sun, causes a wobble in Earth's axis. This wobble shifts the direction of Earth's axial tilt, changing the orientation of the poles and the position of the equinoxes over a cycle of approximately 26,000 years. As a result, the celestial coordinates of stars and constellations slowly drift over time. The effect of precession on Earth's temperature is one of the most important effects. Precession changes the way solar radiation is spread across the Earth by changing the time of the seasons in relation to the planet's path around the Sun. In one part of the precessional cycle, for example, summer in the northern hemisphere happens when Earth is farthest from the Sun, aphelion. This makes summers cooler and could cause ice. If, on the other hand, summer happens when Earth is closest to the Sun, perihelion, it is warmer. These changes help make Milankovitch cycles, which are long-term changes in temperature and are closely linked to ice ages and interglacial periods, happen. Precession also influences the positions of celestial markers, such as the North Star. Currently, Polaris serves as Earth's North Star, but this is a temporary alignment. Over thousands of years, precession will shift Earth's axis toward different stars, with Vega becoming the North Star in about 12,000 years. This gradual shift has implications for navigation, astronomy, and even cultural interpretations of the night sky. Many old societies were very interested in the stars and planets, and the precessional cycle has left its mark on them. In ancient Egypt, the yearly Nile flood, which was very important for farming, began when Sirius rose in the sky. But because of precession, the time of Sirius's rising changed over hundreds of years, so the Egyptian timetable had to be changed. Similarly, both the Mayan and Hindu cultures used precessional cycles in their astronomy and mythology, showing that they had a deep understanding of how the Earth's stellar rhythms work. There are also examples of how precession has changed astronomical systems. Western astronomy used to be in sync with the precessional cycle because it was based on where the signs were along the ecliptic. The zodiacal constellations have moved over thousands of years though, so current astrology signs don't match up with where they were in the sky when they were first created. This difference, called the precessional drift, shows how Earth's connection to the universe is always changing. In addition to its scientific and cultural significance, precession offers valuable insights into Earth's geological history. By analyzing sediment layers, ice cores, and fossil records, scientists can identify patterns linked to precessional cycles and reconstruct past climates. These data provide a long-term perspective on Earth's climate system, helping to refine models of future climate behavior. The influence of the Sun's aging process. The Sun, which powers everything on Earth, is not a fixed point. It ages like all stars do, which causes small changes in how much energy it puts out and how it acts. Even though this changes over very long periods of time, the Sun's aging has big effects on Earth's temperature, rhythms, and ability to support life. Knowing about these effects can help us see what the long-term future holds for our world. The Sun is currently in the main sequence phase of its life, converting hydrogen into helium through nuclear fusion in its core. This phase, which spans billions of years, is characterized by stability in energy output. However, even during this period, the Sun's luminosity gradually increases as it consumes hydrogen and helium builds up in its core. This process results in the Sun growing slightly hotter and brighter over time, an incremental change with profound consequences for Earth. An increase in the quantity of solar radiation reaching Earth is one of the direct consequences of the Sun being brighter. Over millions of years, this makes the greenhouse effect stronger, which slowly warms the Earth. The extra sun energy speeds up the rate of evaporation, improves the water cycle, and changes the way the environment works around the world. This warming doesn't happen all at once or in the same way, but over geological timescales, it can cause big changes in Earth's climate systems. As the Sun ages, its long-term brightening could eventually lead to the destabilization of Earth's climate. Scientists estimate that in about 1 billion years, the Sun's luminosity will have increased by approximately 10%, causing Earth's surface temperatures to rise significantly. This additional heat would trigger a runaway greenhouse effect, similar to what occurred on Venus. Oceans would evaporate, water vapor would accumulate in the atmosphere, and Earth's surface would become uninhabitable for complex life. The Sun's aging process also affects Earth's cycles, particularly the carbon cycle and geological processes. Enhanced solar radiation accelerates chemical weathering, which removes carbon dioxide from the atmosphere and deposits it in rocks. This long-term carbon sequestration affects atmospheric composition and the balance of greenhouse gases, creating a feedback loop that amplifies climatic changes. Besides these slow effects, the Sun's ultimate change into its post-main sequence stages will be terrible for Earth. As the Sun runs out of hydrogen fuel, it will grow into a red giant that will swallow up the inner planets, like Mercury and Venus. It's not clear what will happen to Earth in this case. Some models say it might be eaten by the Sun's growth, while others say it might be able to live, though as a burned-out empty world. No matter what, life will not be possible as we know it. The Sun's final stages will see it shedding its outer layers to form a planetary nebula, leaving behind a white dwarf, a dense cooling remnant of its former self. By this point, Earth's surface will have been completely transformed or destroyed, but the remnants of its geological record may persist, serving as a testament to its vibrant history. Even though these things won't happen for a long time, the Sun's age process shows how stellar development and the ability of planets to support life are linked. Learning about the Sun's life cycle not only sheds light on Earth's future, but it also helps us figure out what conditions exoplanets around other stars need to support life. Scientists can find systems that might have life by looking at how stars change over time and how they interact with their planets. This helps them guess how long those conditions might last. Earth's hidden cycles, mantle plumes, and supervolcanoes. There is a world of great power and wonder below the surface of Earth. Slow-moving forces change the surface of the planet in ways that are both subtle and disastrous. These secret cycles are controlled by mantle plumes and supervolcanoes, which have a big effect on Earth's geology, climate, and ecosystems. Even though these things aren't talked about much in everyday life, they have a big impact on the past and future of the world. Mantle plumes are towering columns of hot, buoyant rock rising from deep within Earth's mantle. Unlike tectonic plate boundaries, where most volcanic activity occurs, mantle plumes originate from the core mantle boundary, over 2,800 kilometers, 1,740 miles, beneath the surface. As these plumes ascend, they create hotspots, regions of intense volcanic activity that are often far from tectonic plate edges. Iconic examples include the Hawaiian Islands, Yellowstone, and Iceland. all of which owe their existence to mantle plumes. Mantle clouds have effects that aren't just limited to areas where volcanoes are active. They help make massive igneous provinces, MIPs, which are huge areas of basaltic lava flows that cover a lot of Earth's surface and form over millions of years. Along with the Deccan traps in India and the Siberian traps in Russia, these areas are linked to some of the most important mass extinctions in Earth's past. Huge amounts of carbon dioxide, sulfur dioxide, and other gases are released during these eruptions. These gases can change the world temperature, either cooling or warming it over time. Supervolcanoes are among the most dramatic manifestations of mantle plume activity. Unlike typical volcanoes, which erupt in a localized cone-shaped blast, supervolcanoes release vast amounts of material in colossal eruptions that can last days or even weeks. These events can eject more than 1,000 cubic kilometers, 240 cubic miles, of ash and rock, covering entire continents and altering the global climate for decades or centuries. The Yellowstone caldera in the United States is one of the most well-known supervolcanoes, sitting atop a powerful mantle plume. While Yellowstone's last major eruption occurred approximately 640,000 years ago, its potential for future activity makes it one of the most closely monitored geological sites on the planet. An eruption at Yellowstone could release enough ash to blanket North America, disrupt agriculture, and significantly lower global temperatures, a phenomenon often referred to as a volcanic winter. Earth's past will never be the same after supervolcano explosions. For example, the Toba supereruption in Indonesia about 74,000 years ago is thought to have caused a harsh volcanic winter that lowered temperatures around the world by up to 10 degrees Celsius, 18 degrees Fahrenheit, and caused early humans to have trouble finding enough people to live. These kinds of events show how geological action and biological development are linked, and they also show how fragile Earth's ecosystems are. Mantle plume activity also influences Earth's long-term carbon cycle. Volcanic eruptions associated with plumes release carbon dioxide into the atmosphere, contributing to greenhouse warming. Over geological timescales, this carbon is reabsorbed into Earth's crust through weathering and sedimentation, creating a natural balance. However, the scale and intensity of mantle plume-related eruptions can temporarily tip this balance, causing rapid climate shifts. Not only can mantle clouds and supervolcanoes do bad things, but they can also do good things. The Hawaiian Islands are an example of how volcanic activity can create new land masses that are home to a wide range of ecosystems. Also, the mineral-rich soils that are made by volcanic ash are very fertile and have been used for farming and building cities for thousands of years. To be able to predict future geological events and lessen their effects, we need to understand these secret patterns. We can now better track mantle plumes and keep an eye on supervolcanoes thanks to improvements in geophysical imaging, earthquake tracking, and satellite technology. In the event of an explosion, these tools could save lives and keep economic damage to a minimum by giving early warning systems. Deep Earth tremors and hidden signals. Deep below the surface of the Earth is a place where things are always moving and doing strange things. Deep Earth tremors are one of the most interesting things that can happen in this secret world. They are small, low-frequency vibrations that don't fit the usual descriptions of earthquakes. These tremors, which usually happen deep below the Earth's surface, tell us a lot about how the planet works, from how plate tectonics and volcanoes work. Even though they aren't directly harmful, they are very important for knowing how Earth's processes work and what effects they have on other things. Normal earthquakes happen when energy suddenly releases along cracks. Deep Earth tremors, on the other hand, are usually caused by the slow and steady movement of tectonic plates. In subduction zones, where one continental plate slides under another, these tremors happen most often. When these plates grind against each other, they create a lot of friction, which causes something called slow slip events to happen. During these events, stress is slowly released over weeks or months. This causes tremors that are too weak to feel with the naked eye, but can be picked up by sensitive equipment. The discovery of deep Earth tremors has transformed our understanding of plate tectonics. For decades, scientists believed that tectonic movement was either abrupt, as in earthquakes, or imperceptibly slow, as in creep. However, the identification of tremors and slow slip events revealed an intermediate category of motion, challenging traditional models and opening new avenues for research. These findings have shed light on how stress accumulates and dissipates in subduction zones, offering clues about the conditions that might precede major earthquakes. Studies of deep ground tremors have important effects because they may be precursors to megathrust earthquakes, which are the strongest earthquakes on ground. Some of the worst earthquakes in history have happened in subduction zones. Examples include the Indian Ocean tsunami of 2004 and the Tohoku earthquake in Japan in 2011. Scientists hope to find early warning signs of coming disasters by looking at trends in the activity of tremors. This could save a lot of lives. Deep Earth tremors are important for earthquakes, but they also tell us about how the Earth's core behaves and how volcanic systems change over time. Some tremors have been linked to the movement of lava below volcanoes, which gives us a look into the processes that cause explosions. In Hawaii's Kilauea volcano, for example, tremors have been used to predict changes in how it will erupt, which has helped improve risk estimates and reaction plans. The study of deep Earth tremors also extends to the field of environmental monitoring. Subtle vibrations can reveal the effects of human activities, such as mining, groundwater extraction, and the injection of fluids into the subsurface during hydraulic fracturing. These anthropogenic signals, while often smaller in scale than natural tremors, provide valuable information about the impact of human actions on Earth's stability. To detect and analyze deep Earth tremors, scientists rely on advanced seismic monitoring networks and data processing techniques. Arrays of seismometers placed in strategic locations record ground motion with remarkable sensitivity, capturing even the faintest signals. Machine learning algorithms have further revolutionized the field, enabling researchers to sift through vast datasets and identify tremor patterns with unprecedented accuracy. Despite substantial advancements, much is still unclear about the origins and consequences of deep Earth earthquakes. Scientists are still not sure about the exact processes that cause these vibrations, how they change in different geological settings, and how they will affect Earth's systems in the long run. These secrets are still being studied, and the final goal is to figure out how the Earth's surface and its deepest parts are connected. Cosmic radiation and Earth's protection. Cosmic radiation is composed of charged particles, primarily protons, electrons, and atomic nuclei, traveling at nearly the speed of light. These particles originate from two main sources: galactic cosmic rays, which come from outside our solar system, and solar energetic particles, which are ejected during solar flares and coronal mass ejections. Left unchecked, these particles could wreak havoc on Earth's surface, stripping away the atmosphere and making life impossible. Earth's magnetic field, generated by the motion of molten iron in the planet's outer core, acts as the first line of defense against cosmic radiation. This field forms a protective bubble known as the magnetosphere, which extends thousands of kilometers into space. When cosmic particles encounter the magnetosphere, they are deflected away from the planet, guided along magnetic field lines toward the poles. This process not only shields the majority of Earth's surface, but also creates stunning auroras as particles collide with atmospheric gases in the polar regions. While the magnetosphere is highly effective, it is not an impenetrable barrier. Some high-energy particles manage to breach the field, especially during periods of heightened solar activity. Solar storms, for instance, can overwhelm the magnetosphere, causing geomagnetic disturbances that disrupt satellites, power grids, and communication systems. Such events serve as reminders of Earth's vulnerability to cosmic forces. There is an extra layer of safety from the weather. As cosmic rays move through the magnetosphere, they hit molecules in the atmosphere, which sets off a chain reaction of secondary particles. This process, called a particle shower, breaks down the energy of cosmic rays so that only a small part of their original strength hits the surface. Without this protection in the atmosphere, the Earth would be hit by amounts of radiation that are bad for all living things. Over geological timescales, fluctuations in Earth's magnetic field have had profound implications for its protective capabilities. During geomagnetic reversals, when the planet's magnetic poles swap places, the strength of the field temporarily weakens, exposing the surface to increased cosmic radiation. While these events are infrequent, occurring roughly every 200,000 to 300,000 years, they raise concerns about the potential impacts on Earth's biosphere and climate. Cosmic radiation also interacts with Earth's climate in subtle ways. High-energy particles can ionize atmospheric molecules, affecting cloud formation and weather patterns. Some researchers propose that variations in cosmic ray intensity, influenced by solar activity and the movement of the solar system through the galaxy, could play a role in long-term climate cycles. While this theory remains a topic of debate, it highlights the interconnectedness of cosmic and terrestrial processes. The problems caused by cosmic radiation become very clear when people do things like exploring space. When astronauts go beyond Earth's safety screens, they are exposed to a lot of radiation, which can hurt cells, raise the risk of cancer, and make it harder to think clearly. For the future of space travel, especially for long-term trips to Mars and beyond, it is important to understand these risks and find ways to lower them. Even while it poses risks, cosmic radiation has contributed to Earth's evolutionary past. It drives evolution over millions of years by changing DNA and introducing mutations, which increase genetic diversity. Cosmic radiation has a complicated connection with life on Earth because of its dual position as a hazard and a stimulant. Extraterrestrial gravitational forces. The Sun and the Moon have a big effect on Earth's temperature and cycles, but the gravitational pull of other stellar bodies also has a big effect on Earth's long-term stability and weather patterns. Jupiter is one of the most important parts of this gravity dance. Jupiter's huge gravitational pull goes far beyond its orbit because it is the biggest planet in the solar system. In some ways, it protects and changes Earth at the same time. On the plus side, Jupiter acts as a cosmic shield, preventing or catching many comets and rocks that would have hit Earth otherwise. Because of its gravity pull, fewer big hits have happened, giving life on Earth a chance to grow. In spite of this, Jupiter's gravitational pull is not simple. It can also bring possible threats closer to Earth by messing up the paths of things in the asteroid belt and beyond. These gravity pulls have sometimes led to hits that wiped out whole species, like the asteroid impact that killed off the dinosaurs. This duality shows how complicated the connection between Jupiter and Earth is. It's a balance between safety and danger. Saturn, while less massive than Jupiter, also exerts gravitational influence on the solar system. The combined effects of Jupiter and Saturn have long been known to create gravitational resonances, altering the orbits of smaller celestial bodies. These resonances can destabilize regions of the asteroid belt and send material hurtling toward the inner planets. Over geological timescales, such interactions have reshaped the distribution of asteroids and comets, influencing Earth's history. Beyond the solar system, the gravitational forces of nearby stars and the galaxy itself contribute to Earth's long-term cycles. As the solar system orbits the Milky Way, it passes through regions of varying stellar density, including spiral arms and interstellar clouds. These galactic environments can perturb the Oort cloud, a distant reservoir of icy bodies surrounding the solar system. Such disturbances can send comets on long trajectories into the inner solar system, occasionally leading to impacts on Earth. Gravitational interactions with other star systems have effects that are even farther away. Alpha Centauri is the nearest star neighbor, and moving stars can sometimes get close enough to change the edges of the solar system. Even though these things don't happen very often, when they do, they can change the paths of faraway objects, which could have an impact on Earth's future environment. Closer to home, the Moon's gravitational relationship with Earth is a well-documented driver of tides and oceanic rhythms. However, the Moon's gradual recession, caused by tidal interactions, is slowly altering Earth's rotation and orbital dynamics. Over billions of years, this process will lead to longer days and potentially more stable climatic conditions. While the effects are subtle in the short term, they highlight the interconnected nature of gravitational forces at work in our planetary system. As part of the Milankovitch cycles, the tilting of Earth's axis is also caused by gravity pulls, mostly from the Sun and Moon. This slow wobble, which takes about 26,000 years to finish, changes the way sunlight is spread out across the world, which affects long-term climate patterns. These cycles show how alien forces change Earth's surroundings over very long periods of time. Supernova events and Earth's climate. A star's dramatic death is marked by these blasts, which send out huge amounts of energy, matter, and radiation. Even though supernovae happen light years from Earth, their effects can be felt all the way to Earth, changing the temperature and environment in interesting and possibly important ways. Supernovae are classified into two main types: core collapse supernovae, which occur when massive stars exhaust their nuclear fuel, and thermonuclear supernovae, which result from the explosion of white dwarfs in binary systems. In both cases, the explosive release of material creates shock waves that spread heavy elements like iron, nickel, and gold into the interstellar medium. These elements eventually contribute to the formation of new stars, planets, and even life itself. The matter that a supernova throws out into space makes the universe better, but the radiation it gives off can have more immediate and powerful effects. One of the most powerful things that a supernova gives off is high-energy cosmic rays, which are charged particles sped up to almost the speed of light. As soon as these cosmic rays hit Earth, they mix with the atmosphere, creating new particles and ionizing radiation. This chain reaction can change the chemistry of the atmosphere, which could lower the ozone layer and make the Earth more vulnerable to dangerous UV rays. The idea that close supernovae have caused mass extinctions is one of the most well-known theories that connects supernovae to Earth's climate. One example is the late Ordovician extinction, which took place about 445 million years ago. Scientists think that a nearby supernova may have destroyed a lot of the ozone layer, which led to more UV rays that hurt sea life, which was the most common type of life at the time. The creation of isotopes like carbon-14 and iron-60 could be another link between explosions and the environment on Earth. Carbon-14 is made in the atmosphere when cosmic rays contact with it. Tree rings and ice cores can be used to find evidence of supernovae that happened in the past. Also, small amounts of iron-60, an isotope that is only made in supernovae, have been found in ocean layers. These results show that supernovae that happened within a few hundred light-years of Earth have left marks that can be measured on our world. The distance of a supernova plays a critical role in determining its impact on Earth. Supernovae closer than 50 light-years could pose serious threats to life, as the intense radiation and cosmic rays could significantly damage the atmosphere and ecosystems. Fortunately, such events are exceedingly rare. Most supernovae occur far enough away that their effects are limited to subtle changes in atmospheric chemistry and radiation levels. The local bubble, an area of space around the solar system that doesn't have a lot of interstellar gas, is thought to have been made by multiple supernovae over millions of years. It is the remains of a supernova. This bubble not only makes the view of the universe better, but it also serves as a warning of how changing and sometimes violent our galaxy is. The lack of thick galactic material in the local bubble may also change how the solar wind interacts with cosmic rays, which could affect how much Earth is exposed to these very high-energy particles. In the distant future, stars in the vicinity, such as Antares and Betelgeuse, might potentially explode as supernovae. Although these stars are sufficiently far enough from Earth to not constitute a direct threat, the study of the consequences of supernovae on planetary and intergalactic environments will be greatly enhanced by the future explosions of these stars. Supernovae pose threats to all forms of life on Earth and beyond. Astronomers can learn more about these stars and others like them by keeping an eye on them. Solar flares and electromagnetic disruptions. The Sun, as the center of our solar system, provides life and energy all the time. But it's also a star that can erupt into massive explosions that might impact Earth in a major way. Among the most powerful manifestations of solar activity are solar flares, which are rapid explosions of extremely high energy and radiation emanating from the surface of the Sun. The disruption of Earth's electromagnetic systems, brought about by these occurrences, and frequently accompanied by coronal mass ejections, CMEs, may pose significant hurdles to contemporary technology while also producing breathtaking auroras. Solar flares occur when magnetic energy, built up in the Sun's atmosphere, is suddenly released. These bursts of energy accelerate particles to near-light speeds, producing a broad spectrum of radiation, from X-rays to ultraviolet and radio waves. The most intense flares are classified as X-class, and their energy output can exceed billions of atomic bombs detonated simultaneously. When a solar flare is directed toward Earth, it can interact with our planet's magnetic field, creating a cascade of effects that range from beautiful to hazardous. The immediate impact of a solar flare is the surge of radiation, which can interfere with radio communications and GPS signals. This is especially problematic for aircraft flying over polar regions, where the Earth's magnetic field is weakest, and the effects of solar activity are most pronounced. During strong solar events, airlines often reroute flights to avoid disruptions in navigation and communication systems, incurring significant costs. Coronal mass ejections, often associated with solar flares, pose an even greater threat. These massive eruptions of charged particles can travel through space at speeds exceeding 1 million miles per hour. When a CME collides with Earth's magnetosphere, it triggers a geomagnetic storm, a disturbance in the planet's magnetic field. These storms can induce electric currents in power grids, potentially causing widespread blackouts. The infamous Carrington event of 1859 is a historical example of such an event. Telegraph systems across the globe failed, and operators reported sparks and fires from their equipment due to the intense geomagnetic activity. We are more susceptible to solar storms than previous generations due to our society's dependence on technology. Especially vulnerable are satellites, which are indispensable for things like communication, navigation, and weather prediction. Their electronic components may be damaged, their operating lifespan reduced, or even rendered unworkable by the high-energy particles from solar flares or CMEs. Everything from international communication networks to monetary systems and the capacity to respond to emergencies would be affected if satellite systems were to be disrupted. Spacecraft and astronauts in orbit are also exposed to increased radiation during solar events. For astronauts on missions beyond the protective envelope of Earth's magnetic field, such as those traveling to the Moon or Mars, solar flares pose a serious health risk. Exposure to high levels of radiation can increase the likelihood of acute radiation sickness and long-term health issues, making solar activity a critical consideration in planning human exploration of space. Although solar flares and CMEs pose big risks, progress in tracking and predicting them has made it easier to lessen their effects. The Solar Dynamics Observatory, SDO, and the Solar and Heliospheric Observatory, SOHO, collect data on the Sun's action in real time, which helps scientists find and predict solar storms. Early warning systems let people who run power grids, handle satellites, and fly planes take precautions, which lowers the chance that broad problems will happen. Astronomers use the study of solar activity to learn a lot about how stars behave and how they affect worlds. Scientists can better guess what effects solar flares and CMEs will have on exoplanets that circle other stars if they understand how they work. This information is very important for figuring out if faraway worlds are habitable and if life could grow in the presence of bright stars. The story of Earth's cycles is one of resilience and transformation, a testament to the planet's ability to adapt and evolve through immense changes. Yet, as we face unprecedented challenges in the modern age, the responsibility lies with us to understand and protect these intricate systems. By learning from Earth's history and harnessing innovative solutions, we can prepare for the shifts that lie ahead. The cycles of the Earth will continue to turn. How we respond will shape not only the planet's future, but also our place within it.